and then we start. I still can do that. Okay, we are more than happy to be here with you today. So it's now biomass become a reality, not the simulation data and like before, etc. So I am Thuy Toan from CESBio, now Globio. And
I'm Sean Cregan from the University of Sheffield.
Yeah, and this morning we will learn about the biomass status. We have the mission status. We have a mission overview, and then the mission performance, and then the mission planning, the flight operation, and then 2 papers about in-orbit commission and analysis and then just we will start with the first one. The first one is the overview of the mission by Björn Roman. So Björn, please.
Yes. Let me set the thing. Okay. So good morning, everyone. So I'm giving this presentation not only on behalf of a lot of my colleagues as well. Some of them are already here also in the room. So Klaus, Antonio, and also Michael Ferringer, the recently retired project manager of Biomass, is also here today with us. So let's move on. So a bit of the outline. So I will briefly discuss, let's say, the primary science questions. So why do we have biomass right now? It's always good to keep in mind. The mission summary, observation, geometry, and the biomass specifics, and a bit on the product layout, and what we plan to do for the level 2 validation approach. So don't expect a firework in this presentation. You will have all day, people will show you the beautiful images. This is just to get us started, really setting the scene for the rest of the day, of today's events. So first, I think it's always good to show where actually biomass is within the ESA Earth observation program. So you see that we've got 3 pillars here. So one is on earth science, one on Copernicus, joint activities with the European Union, and methodology, which we're doing together with EUMETSAT. I think most of you are already aware of this, but it's always good to see where all these, let's say, satellites are located. So biomass obviously is in the earth science, so it's really an earth science flagship. Earth Explorer number 7. We'll have others, let's say, coming soon as well. And then, of course, the Sentinels, they are really in the Copernicus pillar, and also with all the shelter planning there. What is intriguing to see and striking to see that in the 2020s, we are really, I'd say, has been a real revolutionary evolution in the amount of satellites that we've been launching. So the Earth Explorer mission, so biomass is, see here, is Earth Explorer number 7, so really focusing on forest carbon. They see the other ones that were actually flown before, some of them actually are still flying. So EarthCare was just launched, I think, 1.5 years ago. Biomass last year, of course. Flex will go up later this year in summer. And both SMOS, Cryosat, and SWAM, they're all still flying, right? Now coming to the biomass mission itself. So I think it's always intriguing to see what actually was driving the mission itself, and on which grounds it was selected. One of the points is really looking at the progenic CO2 emissions, and then especially the land parts of it. So the land compartments within the carbon cycle. So you see here on the left is basically the sources, and on the right the sinks, so it should be equal. And Sean will be happy to know that this year actually they were able to make them equal. Before there was always a slight difference around, let's say, well, half a gigaton to 1 gigaton per year carbon. So but now at least now been, and there's still from year to year. This is the latest from Friedenstein et al. From the global carbon budget. The latest figures from their paper that was published, I think, in November 25, showing all these figures here. So you see the largest uncertainties, which is important to know, is really still in the land part and land compartment, both in the land use change and the land uptake, where you see, if you look at the relative uncertainties, you see it's 50% from land use change, and for the land uptake is basically a third, right? So these are still gigantic uncertainties in both, let's say, loss and gain of the biomass. So the bottom line is that we still don't understand properly, let's say, the key change processes, and also between, if you look at the land uptake part, even between Felix Stein, the global carbon budget from 24 with respect to 25, you will see actually there the drop in the was going down in from 3.2 to 2.4 gigaton per year. So our understanding that actually the land is not taking up so much carbon as we thought it would be has been reflected now as well in the latest findings. So here you see the overall uncertainty in the land carbon cycle from over the last roughly 15 years. What you see there is that of course both land use change and the sinks. But the important thing to look at is really the error bars that you see here. And you see that over the last 15 years, really, we have not been able to have a grip on the actual uncertainty, on those main uncertainties, to actually try to bring them down. So this is still very much pertinent. So even when the mission was designed or was envisioned in the beginning, since then we've not really progressed in trying to bring down those uncertainties, essentially. Also, the global from the global carbon budget, again, let's say laid a figure here on the regional structure for the decade 2015-2024. You see that the land use change source, and especially on the focus on the right one, so really the land use change and the land uptake part on the right. You see that we indicate the changes basically in biomass. So the intriguing thing on the top figure is to see that between 2015 and 2024, the main emitters are really in Brazil, Indonesia, and the Democratic Republic in Congo, who contribute about half of the global net land use change emissions. So you see here really that the tropics are really the main areas where the interest is. So then what do we know actually about biomass? And this figure on the right is maybe not the easiest one to read, but if you focus on the colors, I will explain the colors a bit so that is clear to you as well. The ground inventory density, so really where we have information on plot information, is shown is shown in orange, where you see there's a lot of, let's say, we know in the northern hemisphere and in the southern hemisphere a bit less, but we have information there on actually plot information. So we have actually some inventories have been done. Whereas in the tropics, you'll see there's hardly anything basically there, right? So let me show this one. Yes, there it is. So you see there, there of course, especially in the tropics, you see that that provides the blue curve, where actually the highest vegetation carbon is present, and also, let's say, where the total forest area is also very large. So this shows that actually there is an actually critical need to have additional information in the tropics. And of course, most of what I already mentioned, there's exactly where the most carbon is stored and where the changes occur. Okay, trying to click for the next one. I'll try this one then. There it goes. Yes. Okay. Yeah. So, in a nutshell, so we really need information on forest biomass, height, and disturbances. I think what I've tried to make clear is that still this information, the crucial information need of this is in the tropics. That's why as well the focus of the biomass mission is there. And it's not only for deforestation, but also for regrowth. And as I showed, we have actually least information and knowledge basically there. Then, of course, what is the effective scale of this change? So we're looking at hectare scale. So actually, we don't have to identify each individual tree there. We're looking at the area where it actually the effective area where those changes occur. What we like to have is, of course, wall-to-wall measurements. So within a specific region, try to capture everything, with also, let's say, repeated measurements over multiple years to also identify changes within the lifetime of the mission. And then the biomass accuracy, what we would try to drive through is try to reach is about 20% at hectare scale, which is comparable to the ground-based observation as of today. Of course, forests go really beyond only the carbon cycle question which I've been addressing here. So forests cover about 31% of the global land surface. And of course, these are one of the most important ecosystems we have on the planet. So they're also important for biodiversity, also natural safeguard, so you can, especially in for example, in coastal areas, but also for economic resources, so for cultural, health benefits, and of course they're also important as they regulate weather and climate. Another interesting fact is that something that we, of course, in our part of the world are not always clear about, is that for woody biomass, of course, is a major source of energy, and a lot of regions in the world are still depending on wood as the main energy source. Especially when you look at in sub-Saharan African households, about 60% still use wood-based products for their cooking, and a large amount of wood removals are really for energy. So still 90% in Africa and around 70% in Asia. So this is something. It's not, let's say, that deforestation is also needed for those communities. So this is something as well to be clear about as well. Then continuing to the biomass mission summary. So what we like to do is to take stock, of course, of biomass in the world's forest and to monitor its evolution. This is basically the overall mission science in a single question. But of course, as primary objectives, we'd like to determine then forest biomass, but also forest height, vegetation disturbances, and regrowth. You see here a nice image of a tree that actually shows that actually, if we would measure above ground biomass, where would we be in terms of carbon, right? So essentially, you could say as a rule of thumb that about half of the dry weight of wood is actually the carbon. It's consisting out of carbon. Secondary objectives, we have imaging of subsurface geology in deserts. This is the beautiful thing of having something at P-band. You'll be able, 70 centimeter wavelength, to be able not only to be able to penetrate through the entire forest canopy, get information about the structural components up down to the forest floor, but also able to see subsurface geology, looking at paleo rivers, actually remains from previous hydrology. Mapping topography and dense vegetation, of course, is also something that this mission will always able to bring, and measurements of glacier and ice sheet velocities. Then the primary objectives here again. So for above ground biomass, upper canopy height, and areas of forest clearing, you will see here actually what are the resolution that we're targeting. Roughly 200 meter resolution for AGB and canopy height. And for forest clearing, looking at 50 meter resolution, so the height resolution actually we try to achieve there. Then roughly one map every 9 months during the int phase, and then global coverage of the forest areas outside these space object tracking radar areas, which I show later, where those are located. So the overall accuracy is about, let's say, as I mentioned already before. So here the intriguing thing that I already mentioned from biomass to carbon, right? So I said 50% of dried woody biomass is about carbon, and then of course going from carbon to CO2, you see as well as in Friedrichstein, you see both mentioning, let's say, figures on CO2 and carbon. Of course, this is very clear. It's about, let's say, factor 4 or quarter, depending on which direction you go, right? So secondary objectives. As I mentioned already, so imaging of subsurface geology in deserts. So we believe, let's say, we can cover, let's say, 5 meter, maybe higher as well, penetration in dry sand. So observation of ancient riverbeds and lakes, mapping of topography on the dense vegetation. So this would be super nice to get really, for the first time, a very consistent digital terrain model underlying, let's say, the forest. It's not able to get, let's say, in any other way. And measurements of glaciers and ice sheet velocity, so variable surface ice conditions. So how are we going to achieve this? Of course, biomass has 3 innovative capabilities to estimate biomass. One is looking at using Polinsar, so SAR polarimetry. It's basically showing, let's say, you get a 2D surface, or what I always say to people that are not used to this, basically you kind of squash in the forest and you get a nice 2D image of the forest. Okay, this gives a lot of information about the intensity at all different polarizations, so you can do already a lot with this. But with biomass, we really make has been designed as an interferometric mission. So with this, I think we also get then with polarimetric SAR interferometry, you also get access then to the height. One thing that makes biomass even more special is that for the first time we have a full, let's say, tomographic phase of the mission. And actually, we're doing this actually today. We just finished finishing the first major cycle. really get, let's say, access to multiple layers within the forest, so we get really kind of a more profile information at different heights. So something about the observation geometry. The sun synchronous, orbiting at 666 kilometers down dusk orbit, so 6 o'clock ascending. We are left-looking system, left-looking radar system. 3-day repeat, 44 orbits. So we have to actually get the baselines. We make sure we have a small east-west drift implemented to get, let's say, to actually have the baselines to get the right sensitivity to height. Strip map operation, 6 megahertz bandwidth, that's all we have there. So we have 432 to 438 megahertz. And satellite roll for swath axis. Satellite repositioning maneuver is after each, what we call major cycle. And so here's on the bottom you see basically the 1-day coverage, and then this is basically the 3-day coverage after 44 orbits. Of course, it's essential then to make sure that we're getting, let's say, this axis. So we have then a satellite roll to go from one swath to the other swath, but of course it's not instantaneous, so you have to first do this 44 orbits, get your baseline, so multiple times finishing those 3-day orbits to get your baselines for a specific swath, then you do satellite roll and you restart this again. And then after each major cycle, then we have to basically jump the swath. Now, okay, what's the best way of showing this? I think showing this by a nice video to explain this. I try to do this every time I present Biomass, really show people how actually the mission is actually operating, because it's definitely different than all the other missions you're basically used to.
Bjorn.
Yes. Yes, thank you. Yeah, I'll be fine. Yeah. So you see here that we actually are able to, finishing the first swath. So we can, after 3 days, we're continuing. So we are collecting, let's say here, the actual stack, either 3 images in the int phase and up to 7 images in the tom phase. What we're then doing is actually having the roll maneuver, and then we're continuing on the second swath, and then continuing the acquisition as we go along for swath 2. The same thing we do for swath 3. Here you can see again after completion of the second swath, we're continuing on the third swath. Okay, and this way we're able, let's say, to what we call then completing the first major cycle. One major cycle consists out of these 3 swaths, which has then all the baselines that you need to actually do the interferometry or tomography. Then after this first thing, then of course we still stay within those ribbons, right? So we haven't done much, only slightly having this east-west drift, but not anything more than this. So what we're doing then, we do a bit of rock and roll here. We're rolling the spacecraft, turning on our thrusters, going to a slightly higher orbit to ensure to speed up, let's say, this east-west drift. And then from there on, we're doing an inverse maneuver, lowering the spacecraft again, and then we are basically continuing. You don't see the inverse maneuver here, but then we're continuing basically again on swath 1, which is an adjacent in the ascending configuration next to the first major cycle, and that's what you see. That's what you see here. So then we're starting again in swath 1, and this way we're able, let's say, to after 7 major cycles, we're actually able to closing the gaps completely and able to get, let's say, a contiguous coverage. That's what you see basically here. Biomass, as I mentioned already, is a left-looking mission, which is, I think, intriguing to understand that actually then, of course, we have in the Antarctic, where we actually are able to observe, we actually have a relatively smaller, let's say, gap basically in at the South Pole, what you see right now. So you see slowly changing now. You will see sorry. Oh, okay, we'll see this later. Mission key fact. So the first civilian P-band SAR in space. So it's fully polarimetric, minimum 5 years lifetime, 17 months tomographic phase we'll be starting with for one global coverage. We started this from the 21st of November last year, and we'll continue this until April 2027. Then we will continue, then we will finish those 7 major cycles in the tomographic phase. And afterwards, we'll continue on 4 years of interferometric phase with around 5 repeated global coverages. Here, what I wanted to say, the coverage worldwide except for North America and Europe. So there are some restrictions on how we can operate until now, which means that we're not able to access Europe and North America at this stage. And this is because we have few space object tracking radars which are operating exactly in the same band And as I mentioned before, it has little effect on the science objectives because our focus, as I mentioned before, is really on the tropics. A little bit on the algorithms and product layout. Yes, I'm nearly done. You see here basically level 1. We have SLC. Then we have a stack product, level 1C, which contains all the products from a given stack, so from a given swath. Then we can go to level 2A, ground notch, forest height, and forest disturbance, and level 2B and level 3 products, which combine into level 2A frames from ascending and descending tracks and provided on a predefined grid at 1 by 1 degree. And then, of course, continuing like this. We have everything is open source, it's available in Biopal, and you can find basically all the algorithms there. Then very quick on the hierarchy of validation. What we plan to do with Biomass is, of course, we want to able to validate the mission, which a few years ago it was almost thought to be impossible because there was very little information, very little validation data available, as I showed before, especially in the tropics. We're starting off basically in validation stage number 1, but at the end of the mission, we really hope that after multiple repeats, we will be able to really get to the end of the validation stages defined by CEOs. How we're going to do this? We're going to use geotrees, and this is a fantastic fantastic initiative, really trying to get this information available globally with the same uniform way of measuring and the same approaches. With geotrees right now, it's interesting to see that every couple of months there are more activities ongoing. Now already there's 43 ongoing, 18 planned. So you see, especially in the tropics, this is well captured nowadays. How they do it is with HGBD estimates at 0.25 hectare using a allometric model. Upscale the plot information using locally calibrated HGBD height model. I will show this in the next graph as well. And then in the end, of course, validate those fitted HGB models. And that's what you see here in a kind of overview as well. Then in the end, of course, the idea is that from all of these geotree sites, we'll be able to use information and put this next, let's say, to a high product of biomass at 1 hectare resolution or HGBD product at 4 hectare resolution. Of course, we're not all of ourselves say biomass, so we're really now addressing now an epoch. I think we're starting now last year at 25 now with both launches of both Biomass and NISAR. JEDI is already there. So we have 3 missions dedicated to measuring forest properties. And of course, there's a major support now from ground networks, from geotrees, as already mentioned. And of course, also other data that is always already available. So it's clear that this combined capability is far greater than the sum of its parts. And this is something that we should be really clear about. My last slide. So satellite lifted off in 29th of April, 11:15 on the Vega C. The Biomass mission is working as expected in orbit. So just a week after its launch, this impressive 12-meter diameter antenna was deployed, and you see the nice footage next to it. LEOP was declared successful on the 7th of May, really starting this 6-month satellite commissioning and calibration phase. And the in-orbit commissioning was fully concluded, let's say, last Friday. So we're now really at a point where we have full scientific expectation ongoing. So with this, I will finalize my slides. Thank you.
Okay, thanks, Bjorn. I think, well, thanks for the overview, which is nice to cover the whole basic structure, but I think we don't really have time for questions on this one. But we'll start going to the performance now, and the next talk is by Antonio, talking about performance after the commissioning phase.
Yes,
that's okay.
Right. Good morning, everyone. I'm Antonio Leanza, and I'm presenting on behalf of these project teams the system performance at the end of commissioning phase. So very quickly, because I guess that the commission is very well known by anyone in the room. So first civilian P-bands are unfortunately only 6 megahertz of bandwidth for the pulse. Fully polarimetric systems repeat past interferometric orbits, and okay, anyone knows this, so better to go quick. Okay. Well, an overview of how the 6 months of commissioning phase has been organized. So the timeline. So as Bjorn said, we launched on April 29, 2025. The first instrument switch on happened on 22nd of May, 2025. And then we have the beginning of the different sub-com phases. I will detail now why we split the entire commissioning phase in 5 different sub-phases. And then the IOC board at the handover, so the handover to the mission manager happens last Friday, 23rd January 2026. Well, why? What you see here in this sketch is basically representing and summarizing the different sub-phases of the commissioning phase. So the difference is mostly in how we operate in terms of orbit and drifting with to have the transponder seen in different locations within the SWOT and in the 3 different SWOT. So COM1 was designed to have no drift in order to see, this was to enable the acquisition with the exact same geometry of target opportunity, mostly for the PSCAL techniques for radiometric stability. And in the same time, COM1 was also a very important subphase because, as I said, Biomass is an unprecedented P-band mission. We know nothing, we have no heritage about how the target behaved at this frequency, so we also use this early phase also to assess the properties of the target opportunity we intended to use for verifications and characterization purposes. Then we start to slowly drift. Actually, was the biggest sub-phases, lasted 2 months. This was dedicated to the antenna pattern characterization using the transponder. For this mode, we started actually with the transponder, which was at far edge outside of SWOT 1, and then in 21 overpasses, we made the transponder position drift relatively to the SWOT, up to reaching again being outside of SWOT 1, but at near edge. This was, of course, to enable the characterizations in elevation at the maximum extent possible. Then the other verification activities have been performed in COM3, COM4, and COM5. In these 3 subphases, the tasks were the same. What was changing is actually, the drift and the SWOT. So we did all the verification activities during COM3 with the transponder in SWOT 1. In COM4, we were in SWOT 2, and in COM5, we were in SWOT 3. In the meantime, for COM4 and COM5, we also exercised for the first time the actual tomographic orbit in a way to have an early collection of tomographic stack already during the end of commissioning phase. Okay, I already talked about this. So this is a summary of the main task in the 5 different subcom phases. All right, as I said, no information about target opportunity. So I said, okay, we need to assess the properties. So we were looking for certain features of the target, certain characteristic. We want to assess this first. And there were many activities related to this. So as you can see here, we did an activities to find suitable area for noise equivalent sigma naught, noise characterizations, the channel imbalance and crosstalk verification algorithms using distributed target, the antenna pattern verification task area, and also the attempt to find some good targets for also IRF analysis, impulse response function analysis. Huge work and really extensive, analysis and data collection. Antenna pattern. So for antenna pattern, we planned 2 tasks. One was the characterization using the transponder. The other one was the verification using distributed target, homogeneous distributed target. So how was designed this task? As I said, 2 months with the satellites to slowly drift in order to see the transponder under 21 different elevation angles. During each overpass, the satellite was transmitting a special timeline. In the sense, we were able to transmit with a single element. So biomass antenna is essentially an array of 2 elements. Each one of the elements is called doublet pattern. What we want to achieve with this task was the characterization of these doublets for both the polarization. So the ultimate goal was to characterize these 4 different patterns, antenna patterns. What you can see during this overpass, the transponder was in what we call the signal acquisition mode. So Biomass was transmitting and transponder was just recording the pulses received by Biomass. Essentially performing what we achieved is a 2D sampling of the pattern in azimuth during the overpass and in elevations along the 21 different overpasses. And then, of course, all these samples have been used to achieve the final form of the pattern by a polynomial fitting with a 5th degree. What you see in the plots below is one example of one of these overpasses. You see the different azimuth cuts with the single doublets and also for the full pattern. So we have the full H, full V, and then the 2 doublets for both the polarizations. And this is what we achieved. So on the left side, you see the polynomial fitting of all the samples collected during this phase. And then on the right-hand side, you see the comparison between the pattern characterized in flight and the pattern which was the ride on ground, which we call the reference antenna secondary pattern. If you focus your attentions on the part which is in the dashed box, that is the part that we actually use for SAR processing. And the matching is quite remarkable. So we had these confirmations that the pattern that was characterized on ground, even though non-directly measured, because due to large size of the reflector, was not possible on ground to characterize the secondary pattern. So we had this hybrid approach of having measurements of the primary pattern, and then to use an electromagnetic propagator to derive the secondary pattern. So for this reason, we said, okay, we need to verify this carefully. We have to characterize this in flight. And we were very happy to see that the matching was quite good. Also for the pointing, what we did is basically to extract principal cuts in azimuth and elevations from the reference antenna secondary pattern characterized on ground and the one measured in flight over the transponder, and by cross correlations to see to estimate this mispointing. Now, it's just one single evaluations over data collected in 2 months, so it's not really does not give you the overview that we need to characterize the pointing. So for this reason, we also added the verification task. But as you can see, in azimuth, the mispointing is basically negligible. We are talking about few millidegrees. In elevation was 1 order of magnitude higher, in the order of tenths of millidegrees, but still well below what was the requirement, which was in both azimuth and elevation, 170 millidegrees. And then on the right, you can also appreciate, after the mispointing corrections, the matching between the pattern characterized on ground and the one characterized in flight. Now, okay, we jump. Okay, all right. So for antenna pattern verifications, we were quite surprised because, okay, we said P-band, we penetrate the forest canopy, so we will not be able to use the rainforest as usual to verify the antenna pattern. So we initially looked into desert area, ice, but unfortunately it was not possible to find homogeneous area with an adequate level of signal-to-noise ratio. So in the end, we were surprised to see that Amazon rainforest also worked for biomass. And what you can see here is the area which was actually used for antenna pattern verification. In the panel, on the left, you see the pattern as measured from the data in the range Doppler domain, compared with the panel in the middle, which is the reference antenna secondary pattern characterized on ground, and on the right with the pattern which was characterized by the transponder. So we did the comparison of this range Doppler pattern with both, and then on the panels below, you can see the residual error, providing us a very, very low round mean square error. So also the antenna pattern verifications, which were targeting full two-way patterns, confirmed that our pattern was pretty accurate. already from the on-ground characterization. It's not working. I pushed, okay. Antenna pointing, so same methodology as for antenna pattern characterizations. We just cross-colorate the pattern measured by over rainforest with the reference antenna secondary pattern characterized on ground, obtaining these evaluations of mispointing in both azimuth and elevations. Also, these verifications confirm that the pointing of biomass is already very, very good. We are talking about, again, in order of a few tenths of millidegrees in both azimuth and elevation, and is consistently stable in this range of values. What you can see here is the time series covering the period from COM3 to COM5, so more than 2 months, saying that it's stable and well compliant. Radiometric stability performed during COM1, as I said, so zero drift because we need to collect stacks with the zero baseline. You can see in the panel which are the target area that we used for the analysis. It was in total 8 sites, 7 sites, and with the cardinality of the stack, which is slightly different because for certain area was also possible to acquire in earlier some acquisition, typically in COM0, because we had a perfect orbit injection, so we were able to start the collection of data already before the beginning of COM1. And then in only one case, which is the case of Durban, we were also being able to add on top in COM2 2 acquisitions. So the largest stack was the one over Durban with 13 acquisition. And this is the result. So we were not sure that the PSCAL was working at P-band. We were surprised and very, very happy that this is the case. So this is an example, the example over Durban. So you can see the time series of the 13 evaluations over Durban, so the stack 13 cardinality. And in the table below, you can see all the summary of the radiometric stability analysis done over all the sites analyzed. And where we were very, very pleased to see that we are much, much better than what was the requirement which prescribed a radiometric stability of 0.5 dB. Here, the worst values that we got was actually over Durban of 16 dB. So much better than expected. Other tasks, these are the verification of IF parameter, polarimetric calibration, radiometric calibration, and geolocation accuracy. For this task, the transponder was used in a different mode, which is called eco-generation mode. For each pulses received by biomass, the transponder transmits back 4 delayed pulses with the 4 corresponding to the 4 different polarimetric responses as is there. In the panel, bottom right, you can see one examples of the nice responses of the transponder, delayed responses, in each one of the 4 polarimetric images. We repeated these activities, as I said, in COM3, COM4, and COM5, corresponding to SWOT1, SWOT2, and SWOT3. Having in COM3 a complete drift, so we covered the entire SWOT. So we actually were able to, 5 minutes, okay, we'll be very, very fast. So, okay, I already explained this. These are the results. All IRF parameters verifications by transponder, all compliant. The ISLR, the requirement was minus 9 dB. We are consistently below minus 9.5. PSLR, we already knew that we were because the requirement is minus 16. We already knew that in SWOT1 we were not compliant by design. This was dealt by request for deviations. And after this, we of course, according to these values, we are compliant again. Range and spatial resolutions are in line with what we expected. So level 1B is 50 meters in azimuth and 60 meters in range due to the small bandwidth that we have, unfortunately. Then the geolocation accuracy is pretty good. You see that in both azimuth and the range, we are always below the 5 meters. The requirement is 25 meters, so we are well in spec. and the absolute calibration factor was computed successfully. These are the time series covering from COM3 to COM5. I just showed an examples of our attempt to perform IRF parameter verification using target of opportunity. Extremely difficult, extremely challenging, because at P-band, finding a point-like target scatterer with a high signal to clutter ratio, giving also the low resolutions, was really, really difficult. So in the end, maybe something else could be done in the future, identifying another target, but was really, really complicated. It was not possible to officially use these results for the verification purposes. Noise equivalent sigma naught, we found this nice area in the Sahara deserts. So you can see, this is indicated by the green box on top. And the final result will go fast because the time is ticking. And the final results, you can see the three profiles of noise equivalent sigma naught for the 3 SWATs at the end of commissioning phase. Also here we have 1.5 dB better than requirement, which was -27. Polarimetric calibration. This was performed using target of opportunity. We selected this area over South America, because we were needing a specific feature of the target. So for channel imbalance, we were looking for area targets showing a sloped topography and low polarimetric entropy. And for crosstalk, we need flat topography and high polarimetric entropy. So there was this assessment. We identified this target, and we used this then for the execution of the algorithms. And the results are, you will see now, outstanding. There is a missing slide. Oh, sorry. How is it possible? Okay. All right. Okay, I can anticipate that for the channel imbalance, we are always better than -35 dB, and for the crosstalk, we are for all the coefficient, we are always below the -45. So it's really, really outstanding. Other IOC task. So we did also the noise characterizations to see if there was a variation in the noise level depending on the brightness, temperature brightness of the Earth. So we also evaluated the transitions from ice to sea and sea to land. And we actually noticed that there is actually a variation in the noise level of 1 dB in the sea ice and 2 dB, more or less 2 dB over land-sea transition. Noise calibration factor, this was successfully computed. The main takeaway is that we have actually a difference between the 4 polarimetric channel and the SWAT. So at the moment, there is just one noise calibration factor which is applied in the processing, but the recommendation from the project is actually to separate and to specify for each SWAT and for each polarimetric channel the noise calibration factor to be applied. Equivalent number of look and radiometric resolutions within the expectation, so everything is as we expected. And for what concerned interferometric common Doppler bandwidth, the requirement was 98%, and we have better than 99%. All right. This was not, of course, a performance parameter, but was impacting, it was really an issue for the verification of the performance. This is just a summary. So what you can see here is actually what we did during the entire commissioning phase was to identify and to evaluate the severity and the distribution over Earth of the RFI sources, and then also to make use of the data to tune the algorithms in order to have the best baseline possible for RFI mitigation. So this slide just summarized the results when you apply the identified baseline configuration for algorithm. On top, you see the spectrum for the 4 polarimetric channel affected by RFI. Just below, you have the spectrum after the RFI mitigations. Then just the panel below are the masks, so you have the full mask, isolated and persistent RFI mask. And then just for a visual impact, what the image when affected by RFI and the one image examples after RFI mitigations. In essence, of course, a lot has been achieved, but the work is not concluded, so I guess that the investigation will go on, and there will be room for improvement for sure, because it's actually an issue. And there is no better conclusion than this. They summarize all the outcomes. So you see all green. So biomass is compliant to all the system performance requirement. For what concerns the radiometry and the polarimetry, we are well beyond expectations. We were amazed by the results. Some issues are still open and will be investigated further during the operational phase, namely, especially the ionosphere mitigations at higher latitudes, which is also, an opportunity for scientific development because we will have a multi-layered, okay, someone else will talk about this, and the RFI. The conclusion is that even though there are still few open points open, the IOC provided a solid and complete base to ensure the required level of data quality and the release to the user. So we are pleased and happy to hand over now the missions to Klaus and have fun.
We are running a bit late, so apart from, I'm just going to say that's very, very impressive. It's a fantastic instrument, beautifully built. Credit to everybody who produced it. So thanks very much for the talk, Antonio. We'll have move straight on if you don't mind.
Yeah.
Sean, Tui?
Yeah, okay. So we are so happy to see that everything is beyond expectation. Yeah, it's really the radiometric stability, the system performance, etc. But now we will go to the spacecraft operations by Jacob Kahn. Yeah.
Thank you very much. Good morning, everyone. My name is Jakob Kark. I'm the Spacecraft Operation Manager of Biomass. I brought with me today Per Ramos-Bosch, the Flight Dynamics Manager. And on behalf of the Flight Dynamics and Flight Control team, I want to give you an introduction on how we operate the spacecraft, how we actually fly it, and especially how we control the orbit, because as you saw already, this is quite something special about Biomass. But before going to the orbit, I want to give you a general introduction. So Biomass is operated from ESOC, it's the European Space Operations Center located in Darmstadt in Germany. And this is where most of ESA's Earth observation missions are being operated from. We call it the Flight Operations Segment, and it means that we take care of a lot of the ground segment, meaning the ground stations that we use to send commands to the satellites, all the data systems, the mission control system, everything on ground that we actually need to monitor the satellite in space. So there we take care of the health monitoring of the platform, performing nominal and contingency operations, and of course controlling the orbit and the attitude of the spacecraft. And also we take care of the space debris, so we monitor the environment and we do collision avoidance maneuvers when necessary. And all of this started already a few years before the launch with the preparation phase, developing all the systems and everything that we needed to fly the satellite. Then last year in April we had the launch, and you see on the photo the mission control team. So it was a big group of people at ESOC taking care of all the different systems that you need to bring the mission alive. And then you already saw this animation also shared by Björn. This was really the highlight for us, was the opening of our large deployable reflector, which we were controlling from ESOC. And then afterwards we continued through the commissioning and now to the routine phase, where we still try to get the best out of the mission for you. So this is where I moved to the orbit control. So you also saw already this morning that during the tomographic phase, we always try to take 7 images to allow the tomographic data processing. And this we do with a repeat orbit that has a repeat cycle of 3 days and a baseline drift in the tomographic phase of roughly 880 meters. And in our terminology, we call this the reference orbit. It's kind of the ideal line that we would like the satellite to follow to implement precisely this drift of the 880 meters to allow for taking the 7 images and building the tomographic stacks. Then, in reality, the satellite, of course, does not follow this ideal reference orbit, but there are certain perturbations that move the real orbit away from the reference, the main one being the atmospheric drag that over time pulls the satellite down, and then we do regular maneuvers to push the satellite back up. So you see here on the bottom plot the attitude of the satellite as it falls down over time, and then we do a maneuver to push it back up. And in terms of the orbit, with respect to the reference, it means that we are off to one side of the orbit, then we do a maneuver, we push it to the other side, and then as the satellite falls back down, it goes back to the other side of the orbit, and we start pushing it off again. So you see that if the ideal reference is a straight line, we always go kind of like we fall to one side, we do a maneuver, we go back to the other side, and this is what is called an absolute ground track control, and it's what many other satellites are implementing. But for Biomass, this is actually not the most interesting thing, how far we are with respect to the absolute reference. Because what we care more about for the interferometry and tomography is the relative baseline control, is how well do we maintain this drift of 800 meters from one repeat cycle to the next. So if you can imagine in terms of actual absolute control, if I'm off by 200 meters once to the left and 200 meters once to the right, my absolute error is always 200 meters, but in terms of the relative baseline, I get an error of 400 meters. So what is actually more interesting is how can we control the relative baseline. And this is what you see here. So actually what's more interesting is not the error from in one orbit from the reference to the actual orbit, but from the actual orbit from one repeat cycle to the next repeat cycle. And how we achieve a better control in this is by aligning the maneuvers that we do also to the 3-day repeat cycle that the orbit anyway has, and doing a maneuver every 3 days. Because like this, what we achieve is that anyway the satellite falls down and we do a maneuver to push it back up all the time, but we achieve a 3-day periodicity also in this, meaning that the absolute ground track, again, if you imagine in the center there would be a straight line, that is the ideal ground track. We still oscillate from one side to the other side, but then if we do the acquisitions over the same geographic location on the Earth every 3 days, it means that we are always on the same part of this oscillations. So if you look at only the red dots, these are acquisitions that are 3 days apart, so they are on the same area of the ground track. They are on the same area of the globe, same geographic location, and actually they are closer together than the overall control of the ground track. So by doing the maneuvers every 3 days, we can achieve a closer relative baseline control. In practice, if you look again at the actual and the reference orbit, it means that yes, you're always off of the reference orbit, but at least you're always off on the same side. So you have an absolute error, but relative to each other, you can control it a bit more accurate by being either always on the left or always on the right, but relative to each other, the error becomes smaller. This is the theory behind it, the idea of how we want to achieve it, and now I want to show you the performance that we achieved so far, because we are already in the tomographic phase now since November. So here you see just a 2-week period from December to show you the real data. And okay, you see the behavior is similar. There's a bit more variation, but still you see the 3-day repeat cycle where we do the maneuvers always to push the satellite back up. And if you look at 2 measurements that are 3 days apart, the relative error is actually smaller than the overall absolute ground track control. In terms of what we try to achieve during the tomographic phase, our goal is to have a relative baseline control of 50 meters, and the threshold is 100 meters. And during the interferometric phase, the goal and the threshold are a bit wider, it's 100 and 200 meters. So this is what we try to achieve. And here at the bottom, you see the plot of the relative orbit control. So this is always showing the difference between one acquisition and the acquisition 3 days before. So this is what we try to keep within 50 or 100 meters. So you see here during these 2 weeks, it worked relatively well, but unfortunately this is not always the case because there are many factors that are making this more difficult. So now I'm showing basically since the start of the tomographic phase, which was end of November, the entire ground track, and you see there are quite some spikes and some excursions, and I will explain to you where they are coming from. But you see also the swath changes. So with the first 3-4 weeks where in SWOS 1, then we switched to SWOS 2 and SWOS 3. So now currently we are still in the SWOS 3 acquisitions. And at the bottom you see the again the relative baseline control, which stays mostly within the 50 and or 100 meters, but not always so. And one limitation that we had that was making this more difficult was the limitation from the satellite itself, from the platform, which is the shortest possible duration of maneuvers that we can do. So you see it here in this period that was end of December, where we kind of have a constant drift in the absolute ground drag downwards. And this is because we could not do the maneuvers as we would have liked to. So we discovered during commissioning that the satellite supports doing maneuvers down to only 3 seconds as the shortest possible maneuver. And here it would have been better to do shorter maneuvers. So you see that actually to stay kind of on a straight line, we would have needed to do shorter maneuvers. Instead, we keep pushing the satellite actually further away because we have to do maneuvers that are at least 3 seconds large. So this we were not particularly happy with. So already during the commissioning, we did some additional tests with the satellite. We did initial analysis on ground, and we developed software updates in the ground control algorithm and on the satellite on board. And now we have a way to do maneuvers down to 0.5 seconds. That here in December it was not yet implemented. That's why you see this effect there. But since last week we have it in place. So now this kind of effect will not appear like this anymore. And this is especially important because the main factor that is influencing the size of the maneuvers that we need to do is the solar activity, which influences how much drag the satellite experiences. And the solar activity is going down at the moment, which means that for the future we will need to do more and more shorter maneuvers. So you see in this plot is a simulation over the entire 14 months of the tomographic phase and the size of the maneuvers that we need to do. And the pink part at the bottom is the 3 seconds, the old limit of the maneuvers. And you see that there are many, many more maneuvers in the future that we would have been not optimal without this improvement. So we are quite happy to have this in place now. Okay, so this was kind of a small excursion, but you see also there are some that are much larger. This comes to what is the main error in the control, in the implementation of the orbit control in general, is the uncertainty in the prediction of the solar activity. Because, like I mentioned, this is what drives the atmospheric drag, and we try to model it to try to predict what the optimal maneuver size should be. But unfortunately, especially now that the solar activity is very high, but also in general, the predictions, they always come with a large uncertainty. And this is why there are large variations. So also there we try to find ways to improve it. The original concept of implementing the maneuvers was foreseeing that well, you need to understand when we prepare maneuvers or when we do maneuver, there are many steps that we need to do beforehand to calculate what should be the optimal size of the maneuver, to prepare the commands, to send them to the satellite so that the satellite can then execute it. And this was originally foreseen to be done over a period of 2 days because there are certain steps and analysis that has to be done for each of the maneuvers. But if you do it over a period of 2 days, it means that you also need to predict what is the solar activity 2 days from now to know what is the optimal size of the maneuver. So clearly it comes with larger uncertainties. So we also implemented new systems and new processes to shorten this timeline down to 1 day, that we can calculate the size of the maneuver only 1 day in advance, using more accurate prediction of the solar activity. And this way we can achieve a better, more accurate control. Nevertheless, this does not always save us. So there was last week actually, there was a strong solar storm. You might have seen it even in the news, if you follow a bit the space news, because it was the strongest solar storm in 20 years. And this, no matter how shortly before we commanded, there's no way to predict it or to know what the size should be. So this is this big excursion that you see here in the end. It comes from this solar storm where the drag that the satellite experiences was basically 3-4 times higher than the average. And even though in general, with the 1 day commanding, we achieve a better performance, if there's a solar storm like this, we always experience excursions. So here the relative ground drag goes up to 600 meters, something like this, the error. So it's quite significant. So these kind of things okay, they are rare, but in general, it's something that cannot be controlled so well. And then there's one more big spike in the middle that I also want to explain to you briefly. So this is a zoom in on this spike that you see here from the beginning of January. And this is because we had a small anomaly on the platform where the satellite went into a safe mode. So it means that the satellite thinks that something is wrong and it switches off the instrument. It goes to a safe configuration. It uses these thrusters to point the solar array to the sun. And this happened, so it was during the SWOS 3 acquisitions, the repeat cycle 1, so the first 3 days were already done and acquired, and then we were kind of towards the end of the second repeat cycle when this issue occurred. And we recovered it from ground, we switched the instrument back on and reconfigured the satellite to its nominal configuration. This was done rather quickly, but because the satellite was using its thrusters to maintain its pointing, it also had an effect on the orbit, and we saw that we were drifting quite far away from where we would have liked to be. So then we were starting to discuss how to recover this, how can we return to achieve the best science. So we implemented some extra maneuvers to push the satellite back down to where for the start of the repeat cycle 4 anyway it should have been. And then from this onwards we kind of followed again the normal relative baseline control. But because the repeat cycle 2, the data was partially missing because the instrument was off for a bit, and the repeat cycle 3 was affected by the strong drift, we were saying, okay, it's not ideal for the tomographic processing in the end. So what we want to do is to, instead of going up to 7 repeat cycles like we normally have, we decided to add 3 more repeat cycles in the end. So what we are now doing is that we don't go from 1 to 7, but instead we go from 4 to 10, which again gives you a stack of 7 images in the end.
Yeah, copy 5.
Yeah, thanks. And the data from the repeat cycle 1 and 2, and also the 3 when we were drifting away, is still available. So maybe it's even possible to do something with it. Now for the normal processing, we use 4 to 10, but still it would be interesting to see what is the effect of this big drift that we had here during the repeat cycle 3 on the scientific data. This is the orbit control. I just briefly want to mention a few more topics that we also take care of at ESOC that also have an impact on the science data return. Okay, I don't have time to go through all of them in detail, but if you have questions on any of those, you can also approach me or Per in the breaks. So one is that for the maneuvers themselves, they also can cause a certain outage in the science, because every time we do a maneuver, we need to stop taking data with the instrument, we need to turn the whole satellite around, turn it back, so it also comes with a certain outage duration. And to reduce this, we are planning the maneuvers over parts of the orbit that are outside of the primary acquisition masks, such that only secondary objectives are affected from time to time. And this is also to minimize the outages. Then we do have collision avoidance maneuvers, so you might be aware that there's a lot of space debris flying around, and from time to time it comes close to our satellite, and then we need to do a special maneuver to avoid it, and this is unfortunately something we can also not control so much. We just monitor it and we react when necessary. So far since launch we had to do 3 collision avoidance maneuvers, and on Biomass it's also a bit more difficult than on other missions, because already we do maneuvers every 3 days, so it means that if you have a collision avoidance maneuver in the middle, chances are rather high that it interferes with one of the maneuvers that you already planned, which can make things worse, but can also make them better, because maybe you can, by just adjusting the maneuver that you were anyway doing it a bit earlier, a bit later, you can reuse it to also avoid the collision. So it's very difficult to say the number of collision avoidance maneuvers, what precisely it means in terms of science impact. For the 3 collision avoidance maneuvers that we had to do so far, they all happen to be in periods where anyway we had to do big maneuvers, and by adjusting the maneuver to do them a bit earlier or a bit later, we could reuse the maneuvers to also avoid the space debris, and there was no impact at all. But okay, might not always be the case. And the other thing that is also making it more difficult for Biomass is just the huge size of the satellite, which gives us a higher collision probabilities. And there also we implemented some new methods to come up with a more accurate estimate of how big the satellite actually is and how it influences the collision probability. And then the last point that is also operational, that is also can have an impact on the science data return, is that instrument, it also, so we have the interference with the SOTR, the space radar zones where we are not acquiring, but we also have an interference with the frequencies that are used by the Indian Space Research Organization for their launch campaigns. And it means that during the launch campaigns, we are not acquiring over India. And there also we have a special planning system in place to reduce the outages only to the areas that are affected over India and only the days where there is really the launch campaign active. So in conclusion, we control the satellite from ESOC and Darmstadt, and we have the relative baseline control, so not just a tube around the orbit, but we try to use the repeat cycle to keep the baseline as accurate as possible, which still there are some shortcomings with the solar storms that is not always perfect, but we try to keep it as best as possible by implementing shorter OCMs and faster commanding cycles. And we really would like to have exchange with you as a science community on the impact that these variations in the baseline have on your scientific applications, especially also during the tomographic and the interferometric phase, because now we have some periods where we see that we can maintain it very well. We have some periods where we have big excursions, either due to the platform or due to solar activity. And yeah, in the end, we control the satellite to get the best out of it for you. So if there's something that you think would be more or less interesting, then please also discuss with Klaus or with me or Pere, and we are very interested to hear your feedback on this. So thank you very much.
Got time for one question, if anyone wants to say anything.
You can now.
If you need to have more fuel now with all these incidences, or is it still in calculation that you had before?
No, so this concept was in place always to do so many maneuvers, so it was already foreseen. And at the moment, we have really plenty of fuel margin left. So this is good news that I'm happy to pass here to everyone, because of the perfect orbit injection that we had and also the general margin that was planned in before, we have a lot of fuel left to keep the mission going for a long time.
Okay, thank you.
Thanks a lot. Thanks, Mark.
Thank you.
The next talk is also about the performance in the commissioning phase, and it's by Marco Di Trocchio. Is that Marco?
Okay. Hi everyone, me is Marco Di Trocchio, and today I will present the results from the Biomass in Orbit commissioning for ARESIS. In this presentation, we will briefly introduce our results and our activities, then we will show some of the results and finally our conclusions. ARESIS supports the Biomass team by performing independent calibration, validation and verification activity. In particular, we are part of the identification for the natural targets of opportunity, radiometric stability verification, antenna pattern verification, and noise and RFI characterization, as Antonio presented before. These activities were fundamental because we need, during the commissioning, to identify some natural targets to calibrate properly the transponder located in Australia, the polarimetric active radar calibration. And all the data that will be presented later on are processed using the biomass processing suite developed by ARESIS for all the products L1, L2, and L3 for biomass. And the analyses are carried out using the SAR calibration toolbox that is an open source SAR data quality assessment tool, and we hope to be used for all the current, past, and future mission later on. And this will provide, according to us, a common reference framework for all the quality assessment for Sentinel-1, Biomass, Roselle, and so on. So, first thing first, we start from this activity, which was the identification of target of opportunity. This activity was fundamental, as I mentioned. Here you can see a brief slide presenting all the regions in the world that were analyzed during this early commissioning phase. In particular, for the antenna pattern and pointing, we expect the desert to behave to be the best candidates. For the noise equivalent sigma 0, instead, we were looking at oceans, and for RX only, and then we span different regions in the world just to acquire receiving only signals. The criteria that will be used, that have been used for the analysis were the following one, which are 3 in particular: the signal to noise ratio, but for us it was not possible to measure directly this parameter because of the large size of the antenna, so we will rely on the in-out band power ratio that will be explained later on in the next slide. The radio frequency, which was actually interference, which was actually a very big problem for the acquisition. And finally, we require that the targets are spatially and temporally stable for us. What we require for the antenna pattern and noise characterization in particular are that targets are both temporally and spatially stable, free from RFI, and the only difference between them two are the level of IOBPR, because for the antenna pattern and pointing we require high level of backscatter, while for the noise we require a very low level of backscatter. We want to sense the noise floor level. Okay, it's not working. Okay, here is a brief explanation of the in-out band power ratio. This is the ratio between the power of the bandwidth of the sensor with respect to the power outside of the bandwidth. So we know exactly the central bandwidth, we know exactly the central frequency, we know exactly the bandwidth of the sensor, and we evaluate it for different targets. Here you have, for example, results for different scenarios, and what we discovered during the early phases of the IOC is that both oceans and Amazon rainforest shows a very high level of IOBPR. That means that what we are looking at is a strong signal coming back to the sensor, while for the Antarctic and deserts, typically we do see this ratio to be very small. That means that we are looking a lot of noise. So deserts and Antarctica will be used later on and analyzed. Unfortunately, when RFI is present, this ratio is not possible to be measured, as for example here in the Gobi Desert. So I just briefly explain you what is the work was huge at the very beginning. So we span across the world very different targets. These are an example. So we analyze in particular for the antenna pattern and pointing deserts and Antarctica. And unfortunately, most of them shows very high level of us was not possible to measure it. In these small windows, you can see 3 examples. For this quick look gives you a briefly example, because you have a quick look of the image on the left, on the central part the absolute data power, and on the right the fast Fourier transform only along the elevation axis. In this way, in particular, the last graph allows you to clearly look at the RFI, what is the huge impact all across the azimuth lines, and for us it was not possible for many targets to measure it. Then the second criteria was the homogeneity of the target. Here you can see an example of different scenarios. So we have that most of the time, if RFI is present, the homogeneity cannot be analyzed properly, while for Antarctica, in which it was not present, was clear that some part of the Antarctica shows a very homogeneous region, as can be appreciated there. And finally, the last criteria is the IOBPR, as I mentioned. But unfortunately, as I mentioned before, we require for the antenna pattern and pointing verification high level of IOBPR, but for all the targets that have been analyzed, or the analysis is corrupted, or shows very low level of IOBPR. here, so you can appreciate the result. So at the very beginning of the IOC, we have to move to different targets. So all the targets fail these pass-fail criteria, and we have to analyze different targets. So we move on to the next slide, showing you an example of the other targets that have been investigated in Russia, in Africa, in Australia, oceans also, because they show very high level of RFI. And the only one that passed all our criteria and proved to be either temporally stable was the Amazon rainforest. So for all the analysis later on that are performed during the IOC, Amazon rainforest was the one that have been analyzed, even if there is some penetration within the canopy. Then we move on to second target of opportunity, which are related to receiving only data takes. In this case, we want to characterize properly the noise floor. We want also to characterize the transition between land and sea. So to characterize the transition of land and sea, of course, we require an acquisition free from RFI or not impacted so much. As you can see, in Madagascar, there is an example of low impact of RFI. So thanks to this receiving only acquisition, we verify also what is more or less the transition of the noise floor between land and sea, and we have a difference of 1 dB for sea ice and approximately 2 dB for sea land, slightly higher. And then we move on to the last target of opportunity related to the noise equivalent sigma 0. In particular, we concentrate at the very beginning on the oceans, but they prove to show very high level of backscatter. So we move on to other targets, and the one that pass all our criteria and were used for the analysis are the Antarctica and Sahara Desert, in particular the one in Libya. So finally, it is a brief summary of all the targets that have been discarded and the one that pass our criteria. In general, what we can say is that deserts shows low level of IOBPR, but they are often contaminated by RFI, so they can be used in uniform areas not contaminated for noise equivalent sigma 0 analysis. For the Antarctica, similar to desert, but they are free from RFI, so suitable for noise equivalent sigma 0. Oceans, we hope to use them for antenna pattern and pointing, but they are temporally unstable, so we have to discard them for this reason. And finally, the forest. High level of IUBPR, free from RFI, and temporally and spatially stable. So forest results to be the best one for this task. So move on to the antenna pattern and pointing verification tasks. After verifying that Amazon rainforest is the best target, we move on to the analysis, to the effective analysis of this one. Biomass implements a very large antenna, 12-meter diameter antenna. So it was not possible to characterize it on ground, and in addition, antenna patterns are not separable in azimuth and elevation. For this reason, it was very difficult at the very beginning to compensate for them. Anyway, at the very beginning of the IOC, we have two antenna pattern models that have been used for the analysis. That are one, which is purely a theoretical model, and another one explained by Antonio before, which is based actually on the repeated pass of the over the transponder, which is called PARC or CDASP in this case. So for the antenna pattern, we start from the processing of L0 product without applying antenna compensation. Here you have an example of disabled and enabled parameter. And we analyze the gamma 0 profile, gamma naught profile. Why this? Because they prove to be independent with respect to the elevation. So for this task, it was fundamental. Then we select an homogeneous region. Here you can see an example of the absolute data power, which is very clear. And later on, we apply a fast Fourier transform only along the azimuth direction. In this way, we obtain what is comparable with respect to the antenna pattern, to the main lobe of the antenna pattern. And then, I won't repeat the results of the mispointing, but thanks to the RASP antenna pattern and the one from the transponder, it was possible first to estimate the mispointing between these models by minimizing the root mean square error between the two, and then to evaluate the root mean square error. As you can appreciate, the difference is almost distributed along the zero absolute difference, and this is fine. That means that the models are very close to what the sensor is looking at. And the results for all the SWOT you have in the top one is SWOT 1, in the middle SWOT 2, and at the bottom SWOT 3. You can appreciate the 2D root mean square error, which was the one presented by Antonio. Results were very promising because the difference is very small, below 0.45 dB. So good results. Then we move on to the noise equivalent sigma 0 results. Today I will present just the one related to the Sahara Desert. Here you can see the noise equivalent sigma 0 as function only of the elevation angle. So all the azimuth lines are compressed and show in what is an histogram. So where the colors are brighter, it means that most of the data are located along this one. And this profile shows noise, actually, in particular the one of the cross-polarized channel, which are located on the right. Results then were evaluated in time, so we re-performed the analysis for different data takes and in time for SWOT 1, SWOT 2, and SWOT 3, and the results were very promising because provides noise equivalent sigma 0 below 30 dB typically, so very good results on this region. And later on, we move on to the RFI characterization and mitigation task, which was the last one we present today. And in particular, what we can say about RFI are actually a lot of things, but in particular, we detect mostly in the frequency domain, and in Asia is very present. The algorithm that has been implemented for the mitigation is the frequency domain statistical detection and notching. And what we achieved with this mitigation is actually, after a refinement, of course, an effective reduction in most of the cases of the RFI, apart of extreme RFI cases, an improvement in the polarimetry and the image usability. And as Antonio mentioned, we decide after the IUC to activate the RFI mitigation in the affected areas presented in the slide of Antonio. Here, in the picture, you can see an example in Russia in particular with RFI mitigation disabled and enabled, and on the right, their polarimetric coherences, in which the main diagonal is the reference intensity, and the upper diagonal, the absolute data power coherences, and the bottom diagonal, the phases. In particular, by looking at the absolute coherence between the cross-polarized channel, you can see how effectively this algorithm is recovering the coherence. Anyway, the work is not done regarding the RFI characterization, so we will collect statistically and continuously characterize this RFI because will be, for the future phases, one of the most important aspects to be investigated more deeply. And of course, we will explore either different algorithms. In conclusion, we can say that biomass system proved to be radiometrically stable. The natural targets of opportunity that we identified are the one showed before. For the antenna pattern and pointing, we suggest Amazon rainforest, and for the noise equivalent sigma 0, deserts and Antarctica. And results were promising because for the antenna pattern verification, we actually verify a limited mispointing of 45 millirad in azimuth and 20 millirad in elevation. And there is a very close match between the theoretical and measured model. And for the noise equivalent sigma 0, we are in the requirement, so the noise floor is estimated to be below 30 dB. And current RFI mitigation algorithms brings actually the improvement, but of course it requires more investigation and will be investigated in the next phases. Of course, the works for biomass is not ended, and luckily we as Aresis will continuously contribute to this project as part of the DISC. So analysis will continue, and we will continuously monitoring and refine all the analysis that we provide to you. So this concludes our presentation. So thank you all, and if you have any question, thank you.
Are there other questions for this? Yep. Hi, okay.
Yeah, thank you very much. Two questions. Just you mentioned that you were investigating. You had this table where you where it said pass or fail.
Yeah.
Is that simply whether you managed to acquire data, or what is the the reason for a fail, for instance?
Okay, the reason for a fail, sorry if I not repeat it, it was actually this one. So for us, we have the three criteria, which was IOBPR, homogeneity, and RFI. And the criteria that we use to pass or fail the different targets are the one listed in this black box. So the IOBPR for the antenna pattern and pointing, target homogeneity, and RFI-free targets, or at least limited RFI for image usability. Instead, for the noise equivalent sigma 0, exactly the opposite IOBPR, so low IOBPR, target homogeneity, and RFI-free targets. So
in the case of the Congo forest, for instance, what was the reason for the fail there?
Okay, the reason for the Congo was that the homogeneity is not met clearly, because the morphology of the terrain does not allow us to identify a region which appears to be as homogeneous as this.
Yeah.
Because in Congo there are a lot of river structures that does not allow us to perform this analysis. We tried, but with different portion of Congo, but it was not possible.
Okay, I mean, that leads me to the second part. That was actually that particular image. Here in the Amazon, I mean, are you using the wetland mask that was so that you can actually mask away the inundated areas, the wetland areas? I mean, it was used for the Sentinel-1 calibration, right? And so here, I mean, you could actually use a larger part of the Amazon for calibration rather than just a very small window if you would use that mask.
We would have liked to use all the picture, but we are not applying a mask actually. It is an improvement that we will provide, so we just analyze a small portion of an image, but actually it is not so small portion. They are actually kilometers, even if they seems to be very small. So actually we are not applying mask, and we are analyzing all the data. So we are including either errors, and luckily either with this inclusion of errors, results were very promising.
Okay. Right, thank you.
Thank you.
Thank you. Thanks, Marco.
Thank you so much.
It's a pity that we don't have enough time for a question, because a lot to be asked, but the presenters are here, and all the team from ESTEC, from ESOC, and from Aresis, Polinsar are here, so you can approach them. Yeah. And the last paper of this morning is again about the radiometric stability of biomass data, and this time using permanent scatterers, a methodology that Professor Fabio Rocca talked about years ago, but now we'll see the result. Thank you.
Thank you very much, Tui, and good morning, everyone. So this work was actually done by Marco Manzoni, who is a researcher at Polini, but I will be presenting on Marco's behalf. So we are talking about permanent scatterer calibration What it is about? Well, the key idea is that we want to use stable natural targets, if any, to monitor radiometric stability over time and eventually to correct it. So the PS, the use of permanent scatterers dates back to the 90s, more or less, for interferometry. And then the idea to use them for radiometry came out more or less 15 years ago, nearly 20. Now, what is a permanent scatterer? Well, it is by definition a target. It's typically a small target because we work pixel-wise, so it's like a man-made target or a rock, something that is, let's say, something that keeps a response that is stable over time and also over space, meaning that if we change baseline, the response shouldn't be affected. Now, if such targets exist and if we detect them, then the idea is that we can use them to track the instrument gain over time. Now, this was demonstrated some 15 years ago with ERS2 data, and it worked beautifully. The accuracy was to within a small fraction of a dB. This was validated with transponders, so we know it works, but of course that was C-band. P-band is a completely different story, and I would say that until Biomass, this was a dark mystery, so we didn't know at all whether we could use or not this methodology. So now, how it works? This is just to keep it simple. Just imagine that we pass 4 times, and that we have in this case 4 PSs with radar cross section B1, B2, B3, and B4. Now we suppose that those radar cross sections are stable, they are permanent, and but the system can change its gain, so its total gain, so it's A1, A2, A3, and 4. And so of course you read the product between the two. So those are the data. Oops, I did something bad. Okay, so those are the data that you have in your hand. Now, you can stack those data into a matrix, and this matrix has a beautiful algebraic structure. It is a dyad, so it is an outer product between 2 vectors. One vector is the amplitude of the PSs, and the other vector, A, is the instrument gains you are looking for. So of course the decomposition is unique up to a single constant, which means that we have a theoretical basis to track the gain variations. So we are just talking about the variations. We cannot do an absolute calibration. Now, the devil is in the details. So this simple approach will not work in practice because you need to account for noise. So this is a model that accounts for, well, let's say for 2 more things. One is the noise, this W, which depends on clutter and thermal noise. And also you have the phase, so each PS comes with a phase that changes for each PS, and it also changes for each acquisition. So based on this model, we want to estimate this AN, which is the instrument gain. It's very reasonable that the performance depends on how many PSs you find and how many images you have, and of course on the quality of the PS. And this is a very simple formula, so the variance within which you can estimate the gain is given by the inverse of the signal to noise ratio, assuming it is the same for each PS, and number of PSs. Now, how do we model this? For the noise, we assume it is a circular Gaussian, which makes sense, with an unknown variance that depends on the PS. It is unknown because it does depend on local clutter, which you do not know. And then, basically, what we want to do is to cast the problem in terms of a maximum likelihood estimation. So basically, we want to maximize the probability given the data. Now, we have a lot of parameters, so we need to simplify it a little bit. It's easy to see that now it's easy to estimate the phase. So if you maximize this with respect to the phase, and then you plug this expression into the probability, it turns out that you can work with the magnitude. So basically, we pass from the first probability to the second one. The big difference is that we no longer work with the complex data, we just work with amplitudes, which simplifies everything a lot. So we are very, very happy about this. And then basically you can notice that it would be easy to estimate the gain and the PS amplitudes if you knew the variances, or the other way around, it would be easy to estimate the variances if you knew the other parameters. So basically what we do is we iterate. So we estimate one and then so on, and after a few iterations it converges. I haven't mentioned until now that we also need to detect the PSs. Of course, we do not run this for every pixel. We need to select the pixel where we think there is a PS. This is done, well, according to the literature, this is done with the dispersion index, the mu over sigma. Mu is basically the average magnitude for each pixel over a time series, and sigma is the variance. So as simple as that. A good PS has a very high dispersion index because it means that its average is some number and its variance is ideally 0 because it is permanent. So there is no variation. It stays constant. What is difficult here is that this index is not normalized, so it's always a bit embarrassing to set a threshold. So instead, we work with the log likelihood index, which is a transformation of it. This is normalized between 0 and 1, so it's easy to set a threshold. Now, results. Results from COM1. COM1 means that the baseline was nominally 0, so we are only concerned with the temporal stability of the PSs. In this case, we did not apply Faraday correction, not because we are lazy, but because, let's say, during COM1, so we were in a very early phase of everything, so we wanted to try one thing at a time. And also the processor was not perfect yet. And so for this reason, we use the span. So instead of working with a single polarization, we use the quadratic sum of all the polarization. And now some results. This is Durban. All the red points are detected PSs. In this case, we have 475 PSs with 11 images, and this is the stability. Take a look at the scale. In dB, it ranges between minus 0.3 and plus 0.2 dB. So it means that the instrument is actually very, very stable. The amplitude of, so this amplitude here is the predicted variance, which depends on the signal-to-noise ratio of the detected PSs and the number of PSs. I have many examples. They are all more or less similar. This is Brasilia. Again, we are on the same order. Nairobi, ascending. This is nice. There is an outlier in this case because RFI mitigation was turned on by accident, and the algorithm noticed it. Nairobi descending, a bit less stable, but always very stable in general. Baku and, okay, they're all the same, so I think that I can skip it. This is just to summarize and to confirm also what Antonio said, that we are much better than we thought. So very good news. Let me tell you that Delhi is missing because there were a lot of RFIs, and it was the impact in that case was so big that we couldn't apply the algorithm at all. Now, some results from COM4. This is important because in COM4 we have the same baselines as the tomographic phase. So we are also testing the algorithm, the possibility to apply this methodology with a baseline. In this case, I told you that we improved along the route. So we have improved pre-processing. Further rotation in this case was applied, and so I can show you results using single polarization. Unfortunately, I do not have the same area as before, so we are in the vicinity of it. This is the dispersion index for the 4 polarimetric channels. On top, you see it ranges between 0 and 8, more or less, and this is its normalized version, the log likelihood. For the span, you see that it's very close to 1. It means that we are detecting a lot of very stable target. It goes a bit down for the single polarizations. It's also a statistical effect because you have fewer looks, if you like, but overall it's very high. Notice that the scale ranges between 0.8 and 1. Okay, this is just to show you what happens. Sometimes we have RFI, which in this case produce a decay of the dispersion index. And this is to show you the PSs that we detect. With the span, we can detect more, but also in HH and VV, we can detect many. We don't find PSs in cross-pol. It's also a matter of the threshold, of course, but let's say for this threshold that we deem to be safe, we couldn't find it. This is just nice. So we have a railway, which shows up very, very clearly. And in this case, it's nice to see that the railway does not appear in cross-pol. It appears very, very clearly in HH and VV. And the PSs that we find are complementary, meaning that we see some PSs in HH that do not show up in VV and vice versa. And then, and this is my final slide, this is the result of stability over the 6 days we have using span, using HH, and using VV, again with their variance. Now, okay, they're not perfectly the same, but again, take a look at the scale. We are in between minus 0.2 dB and 0.2 dB. So basically, also with individual channels, we are seeing that this instrument, once calibrated for further rotation and the rest of the polarimetric calibration, is really very, very stable, which is very good news. This is just to conclude, so it's just a summary of what I just said. It seems that the instrument is very, very stable. It seems that PSCAL is working, so now we know that there are PSs at P-band too. We continue to apply this methodology for the rest of the mission lifetime, and possibly so now that we are gaining confidence, we can perhaps pass from not just monitoring, but also to calibrate if need be. And this is it. Thank you very much.
Thank you, Stefano. So we did not know, but in the past, from many, many years, there was a question: are there enough PS, permanent scatterers, at P-band data from space? And nobody knows. And then now we can see that there's plenty of those.
Yes.
Even then, our colleague Fabio, he said that we can take a fridge, put in the crossroad in order to see the permanent scatterers. Yeah. Now, plenty of them.
Yes.
Yeah. Okay, so
it's a solved mystery now. Huh?
Yeah. Okay, you have maybe one question? Yeah.
Klaus. Oh. Sorry, Klaus. Yeah.
So,
yeah.
could you use the permanent scatterers to observe the the gain over the orbit, if you have a variation of the gain over the orbit for thermal effects or anything similar?
So the gain over the orbit, so the problem is that as you move along your orbit, you see different points. So it will always be, I would say that it will be relative to the previous time you passed, basically. So.
Okay, so Costas.
Do we know something about the life expectation of this PS? Can you compare them in the tomographic phase with someone later in the ferrometric phase?
I don't know yet. I don't know. It is a super important and interesting question with practical implications, and also physical it is super interesting, but I think that we need time. So we just need to maybe the best thing that we can do is to, now that we are in the tomo phase, to look for data that we acquired during COM1. This would make a time lap of few months, but we haven't done it.
Yes, the sessions end, but maybe I have the last question about the RFI. Now that we fly a lot more in Asia and in the desert, is it any chance to negotiate with people for illegal sources of RFI? The RFI in Asia, for example.
Okay, yes, there are a lot, especially over China. I think it's the worst place. If there is a way to negotiate, I'm not the right person, but maybe Bjorn and Klaus know better.
Okay, so.
Okay, well, thanks very much. Oh, sorry. Is there another question there?
I would have answered to TUI, yeah?
Yes.
Go on.
So if they're illegal, of course, you can take action against them, but at the event we have a shared frequency band, so most of them are not illegal, and then you cannot do anything. Huh?
Okay.
Thanks, guys.
My master is illegal. Yeah, okay.
Most of the RFI seems to be related to military activity, so we don't have the priority.
Okay. So.
Okay, well, thanks very much for...
Do we have time for one more question?
Yeah.
Go on then.
Go on.
I was just wondering if you did the comparison between bands. So if you compare the number, I don't know, from C band to...
No, we didn't. No, it's a nice study, but we didn't. You can do it.
Yeah.
Okay, I mean, it's already been full of interesting things.
Yeah.
Very nice session, but there's plenty more to come.
Yeah.
So get a coffee and be back here for...
Maybe I have a less work, and then but behind the beautiful biomass images, so people are impressed by the images. So the Pauli images are colorful, beautiful. We see a lot of things. But we can see now that how challenging it was to achieve the objective that we set up many years ago without knowing whether it will work or not. But now it's okay, so we can celebrate the biomass. Okay, thank you. Okay, so last word. You have to fill in the questionnaire that Klaus talked about, the questionnaire.
working?
No, no,
Yes.
it's already,
It's always on.
It's on by default. Now it's off.
When it's ready, it's off. It's on. It's on.
There you go. Maybe being in front of you. Here we are. Those sessions. Here we are. There's 11. These are our Biomass first results one. First one is the Costas. Yeah. Maybe start the introduction. You start the introduction and then maybe Costas at the same time, right? First page.
Yeah, yeah.
6 months. Surprises and challenges.
So good morning to the second session. I'm Michael Fehring. I was the project manager for this mission, and Björn Rommen was and is the project scientist. We are happy to see you here, and I'm personally very pleased to see the first results. I've had the pleasure to work with a group of scientists throughout many years. It was a very fruitful and wonderful collaboration, and it's good to see the wider community today. So let's jump into it already now. The first talk is by Kostas. 6 months into the mission, surprises and challenges. There were, technically speaking, fortunately, not so many surprises, but scientifically there were quite a number. We will hear it. Kostas, please, the floor is yours.
Michael, thank you. So good morning also from my side. Welcome to this exciting biomass time. And we had the privilege to be from the very beginning involved in the mission. So we had now 8 months the availability to look on the data from the very beginning. And of course, if it comes to speak about surprises, I think I could speak the whole day. But we decided to focus on 2 unique things for biomass. The first one is the penetration. P-band, so 70 centimeters. No other sensor ever before penetrated so deep in ice, forest, sand as biomass before. And the second unique thing is polarimetry. Biomass is the first sensor ever with its image is a polarimetric one. So the combination of the two have the challenge, plus interferometry of course, to allow us to learn a lot for the next mission. So let's start with ice, penetration in ice. And one of the biggest surprises, so I try, is the evaluation of COM4 and COM5, so 2 of the 3 swaths over a big part of Antarctica. What you see here is the polarimetric complexity of the scattering. And of course, you imagine that you penetrate, you have a volume scatterer, and you expect that the polarimetric complexity is high. But that's not the case. You see, except of the glacier areas, of the ice shelf areas, polarimetry is very powerful. So you have deterministic scattering processes. Surprises number 2, it's surface scattering. So where do you expect? What happened with the penetration of P-band? And the solution, of course, is always hidden in the details. So you penetrate, but ice is a layered medium. And you have a set of surfaces. So here is the top of the ice, and then you see in the sound data the distinct layering of the levels. So you have superposition of surface scatterers, so always the same scattering mechanism, so they add up and provide this low polarimetric complexity. So the door is open to explore polarimetry in all its power over ice. Much more interesting, this image here, anisotropy of polarimetry over ice. So the significance of the secondary scattering mechanism, or in other words, how noise corrupted your polarimetric space is. And you see everywhere where entropy is low, anisotropy is high. So this means that polarimetry is powerful here, is super powerful. Important point here, look the modulations here. From where are coming the modulations in the anisotropy? So first understanding is that you don't, of course, see the bedrock, but you see the modulation of the bedrock on the ice layers above it. And then you see from the bedrock standing up what happens. You always have a smoothed version of the bedrock. And this is indeed what comes up. And a more convincing argument and a more full analysis about exactly this is presented by Patricia on Thursday. So now let's start to zoom in. So polarimetry and penetration. So this is azimuth, this is range, and you see a polarimetric image over ice. So the first, so it's a glacier, so it calves here, and here's an ice sheet. And the first striking thing is this zone here. You see coming from the sea to the ice, you have a surface scattering area, and then it jumps out to a dihedral scattering. What is this? That's penetration. And polarimetry allows you to see this. You see you are coming here, you have a surface scattering, but you also penetrate. You are at p-band. And you have a dihedral interaction. And this one increases the path in the ice, and then you start to see from here the dihedral scattering component. So you can start to think, you can calculate ice thickness. In this case, you are coming up to 100 to 120 meters, depending on the electric constant, what you choose. So challenge number one, how far can we explore the water-ice interface through penetration in biomass? Very impressive, entropy. So, and then you see very clear the low entropy zone here associated to the surface scattering. And then when the dihedral comes back, you start to have the superposition of different scattering mechanisms. Now, if you look more in the detail, you start to see all these dihedral contributions here on the border of the ice sheet. It's again a dihedral contribution coming because of the penetration of the biomass through the ice layer. Next dial, here, iceberg. And if you see on the iceberg, you see you have a surface scattering on the top, but then beyond the iceberg, we have a distinct line, a dihedral line. And this is the same effect. So you have the surface scattering, and then you have the dihedral, which is faced later on. So you can explore this to measure the thickness of iceberg, and Georg will show you how far you can play this game in the case of biomass. So, and icebergs are everywhere. Everywhere in biomass, you see the penetration, you see always this shadow effect with very distinct and different polarizations. So that's a unique combination, penetration and polarimetry in every image. Good. Now, we stay there and we look further. So what you see here is the transition of an ice shelf to the inland ice, and you come here over a rocky area. So you're coming here from the ice shelf, the rock, and you continue. So polarimetric properties, you see many colors. So more spectacular, polarimetric anisotropy, the importance of the secondary algorithms. And then suddenly you see something which you didn't solve any sensor before. Why? Because first of all, you have this ability to penetrate. You are not disturbed by the surface roughness, and you have an instrument with a super good noise equivalent sigma 0. So look on these patterns here. So what you see is the fraction of the ice, and you can visualize it even better looking on the left-left, right-right face of polarimetry. So what you see here is a measurable of the line of sight orientation of the scatterers. And what you see is the dynamic of the ice, how ice reacts under this elastic deformation process occurring there. And of course, crevasses, super spectacular. So you see here, p-band, very strong dihedral contribution, polarimetric entropy, and the firework. Again, polarimetric line of sight orientation. And what you see here is the deformation, the different deformation of the ice scatterers or volumes or whatever it is, as you move away from the tension zone. So that's a treasure. Good. Second scatterer to look like. We move from ice, which will be a new space to explore in terms of polarimetry, even before adding interferometry, and we move now to forests. So, and of course, we expect that p-band penetrates in forests, but we said penetrates more. And the funny thing is, at the end of the day, the more you penetrate what you find more, the more water you find. So this is a number of acquisitions of come started on very early. You see, we're already in May. It's about 1 month. 1 month tropical forest somewhere in Amazonia, polarimetry. You look and you say, yes, it looks interesting, it looks fascinating, but it looks similar. Where are the dynamics? So and now we start to look on the interferometry. So this is 3 days, 6 days, 9 days, 12 days. What do you see? You see water. You see how we're starting from here. Here, this river here has not changed in the scatterers, and suddenly, this is the H polarization, you start to have a decorrelation here. The correlation here, this river is whatever it is, this is calm. It increases, and then it starts to go back again. Coherence come back. What you see water dynamics. But now this river here starts to decorrelate, and if we continue, you see that you are sensitive to the water level, in this case, under the vegetation. So you have an instrument which allows you for the first time to associate, to measure water dynamics under dense vegetation. Where? Everywhere. And where is polarimetry? So this is the HH coherence rhyme. HV, boom, diedrals is gone. And then you see suddenly that also here, the same surfaces, it goes down and up, and from up goes down. You see formally the water flowing through the image. And of course, HV. So the sensitivity to this. Now, how different is polarimetry formation? Just superimpose the polarimetric coherences, and you get this. So polarimetry gives you colors, colors of physics. And then you see that, of course, the biggest contribution always is dihedral, but we have a lot of green areas. We have a lot of cross-polarization. We have a lot of areas where cross-polarization gives you the highest coherence and the high temporal stability. And even if it's only 6 megahertz, at this scale, it is just beautiful. Good. So this is now always the coherence with respect to the master. You see over 1 month, in principle, coherence is relatively stable, except of all these shadows here. You have the water. If you penetrate, at the end you find water. This you have to accept and to explore. And on the other side, you have these shadows here. So what happens now if I make only the 3 days coherences and compare them to each other? Then you end up to this. So of course, the dynamic here is less, is always with respect to the previous 3 days, but still you see a very dynamic signature. So the fact or the understanding is that what we assume a scatter to be stationary for a number of acquisitions is just not true. So if you penetrate, if you start to see water, if you start to see all this effect, then the assumption that a scatter from acquisition to acquisition remains constant is not necessarily given. So we have a very dynamic environment, and this may be a burden, but of course it is the big challenge to start to explore this, to make the next step in our understanding. So now, how we can explore the dynamic changes in this? So you can say temporal decorrelation can be wind, can just only move the scatterers but not affect the scattering center. So there are possibilities, so develop it for surface, so for soil moisture on surfaces, to apply this phase. You try to use 3 interferograms to make a cyclical relationship, and as long as the phase center heights are not changing from acquisition to acquisition, then the circle always ends at the same point. But if something changes, then you obtain a phase offset. This is called phase triplets, and the advantage of these techniques is, of course, that you are independent from propagation effects. And now we start to see how this behaves on always 3 days. So 3 acquisition, 1 phase triplet, 3 acquisition, a second phase triplet, and now we can start to scroll through. Of course, you see the water, but more important, what you see are all these shadows here. So what is this? These are the shadows on the coherence map, and this is rain. This is rain, and we discover that a rainforest is called a rainforest because it rains every day. So, and what happens if it rains? So if it happens if it rains, it's just that the canopy becomes more wet, and then the phase center of the canopy goes up, and you see also less scatterers. And exactly this effect is what causes you now these shadows on the coherence map. So it is not the stability of the scatterer. So you can track everywhere here. Now I think I have my difficulty to point and to click, but if you look here, you will see that the strips are rain. So we have an instrument that measures also rain, if you like. So good. Then, now, this means that now in terms of inversion, so I will not speak a lot about this, is that our assumptions about how the scatterers behave and how stationary they are in time, they are wrong. And this is always good that you learn out where you are wrong, because this is the only way to explore something new. So if you have always right, then you don't learn anything more. Exactly this. And this is one of the biggest challenges which we face if it comes to make forest height inversion, tomography, and so on, which will be a number of presentations in the next sessions. So, one more example. Phase COM5, baselines, interferometry with polarimetry in baselines. And again, a dynamic area. 6 acquisitions, so we are now in October. Towards the end of the commissioning phase, a dynamic area in Nigeria, and unfortunately you don't see it here. Here on the bottom is the delta, and deltas in water are always very dynamic areas. So this is polarimetry. Again, you have the fact you don't see big differences. If I now start to look on the 3 days in the ferrometric coherence, then I see a very dynamic effect. Especially here on the bottom part, on the delta, you see a change of the colors. The stability of different scatterers in time is changing as an effect, of course, of the water. And of course, you have the rain and you have your RFIs up here, which is part of the mission. Good. Now, I would like to focus on the delta. And what you see here is the polarimetry across these 6 acquisitions. And if you ask you, do you find the difference? Then I think that you have to look very in detail. If I look on the interferometric coherence over 3 days, then you see a very dynamic image. You see scatterers, which are different categories of scatterers, are different stable over time. So, what happens? Where is polarimetry? The fact is that these changes occur on the surface. So you penetrate, you see the surface. But on top of the surface, you have a volume, you have vegetation. And polarimetry in vegetation is, as the volumes which we expected, decrease the ability of polarimetry. It increases the entropy. It increases the depolarization. So this means that polarimetry by itself has not, because it is only a 3-dimensional space, has not the ability to resolve this complex scattering process. But you have interferometry, non-zero based interferometry. Interferometry can help. Why? Because interferometry allows you to separate volumes from surfaces. So you can use interferometry to separate the ground from the volume and then look on the polarimetry of the ground. And then you start to see just miracles. You see the dynamic change of the polarimetry of the ground as a function of time, and it maps what you see on the coherence maps. And then you see why this is going hand in hand, because polarimetry allows you to understand what happens in your chains. So it understands to articulate and maybe to explore also these complex patterns of chains, which we have no chance if you just say, wow, I have a non-stationary scatterer. So that's maybe the best bullet which we have to fight this non-stationarity, which of course is important and critical and missing understanding about how things change on our planet. Good. Last, I'm at the end, almost. So next thing. So we spoke about low SNR and high SNR, noise, low noise equivalent sigma 0. And before the mission, everyone thought if you look on surfaces, it will be noise. So for P-band, everything is smooth. So surprise number 1 of the very early days is just the polarimetry over oceans, over water. And you see a lot of structure. So where we are here, we are in the Philippines, and Philippines is very far, very close to the equator. So 2 things. So the instrument is, from the noise perspective, so brilliant or so good that allow you indeed to start to explore polarimetry over surfaces. Second one, what is the anomaly here? The anomaly is CMATS1. You see the stripes. We are in the morning, we are in an ascending path, we are in the Philippines, in an area where it's forbidden to have scintillations, and then you see scintillations. So this is the transition to the next presentations. So the next big discovery comes from looking of ionosphere. And where is the link between water and ionosphere? It is the layers. And Stefano will speak later. One of the very interesting and special problems and big challenges is to explore the sensitivity of this low frequency to the ionosphere in order to understand better the dynamics of the ionosphere. So what you see here is a scene. This is Gabon is up here, and then we go from the south to the up. It's acquired in the morning, so 6 o'clock in the morning, local time, and it was affected by ionosphere. And this is the pattern of the ionosphere, what you see there. And the interesting part, of course, this is what we expect, ionosphere on higher levels, on higher layers, which are aligned to the geomagnetic field, but you have this pattern here. And this pattern is probably a lower ionospheric layer, is a sporadic E layer, which is oriented, probably not in the direction of the geomagnetic field, but is wind-induced very often. And then you see these two layers of the ionosphere, which of course for interferometry, it is a challenge, but from other sides, it is a unique signal coming from the ability of this sensor to operate at this low frequency. And as a last image, also here, so again, we are in an ascending path in Amazonas, and you see this ionospheric pattern, so you expect that everything is aligned in azimuth, if it was the F layer, but in this case, it's probably again the sporadic E layer, which Biomass tries to convince us that it's not so sporadic as assumed. Good, and here we are at the end, and there is no future without past. And at this point, of course, polarimetry has a long history, especially in this workshop, but even before this workshop. And before closing, I would like just to point out two persons, so which were influential and was supporting to reach this point today. And the one was Wolfgang Martin Börner. So he had the vision to understand how exciting a mission will be when you are able to measure for each pixel the scattering matrix, the Börner machine. So now we have a Börner machine. And the second one is Pascal, which left us before seeing, he was working a lot for P-band, a pioneer in polarimetry, and he left us before seeing the results of this mission. So with this, you have always remember the past, but look in the front. And the future is great. Thank you for your time.
Thank you, Kostas. Any question from the room, pressing question before we move on to the next presentation? Yes, I see that. Yes. Sean, please.
Kostas, how thick would the ice layer be, a floating ice layer be, to get the double?
120 meters, Georg will results of the iceberg up to 150 meters.
But how thin could it be and still get it?
How thin they can be?
Yeah. Would you still get the same effect if it was just 6 meters?
So there is a presentation of Georg, very Italian. So we think we see here hundreds of meters.
Right.
So it is everywhere. We have this strong dihedral effect. These are the most clean examples. There are many examples which are not very well understood, but this is a very exciting combination of penetrating and having the ability to separate different scattering mechanisms. And in this scenario, they are relatively orthogonal, so you are very powerful to do this.
Okay.
Thank you. Thank you, Kostas. One more question, yes.
Kostas, thanks a lot. A very nice presentation. Just would like to understand that it's not stationary that you saw on the target. What will be the impacts on your inversion model for the forest high end?
So Yes, of course, it makes temporal decorrelation a bit complex. So temporal decorrelation introduces also a phase. And then you have to think how you address this. So, and at the moment, our understanding is that polarimetry is the one tool which allows you to address this. But this is still an open problem. You can still ignore this and assume that temporal decorrelation is a scalar thing, but still there are phases involved there, which not in the perspective of inversion, but trying to understand them and to model them is, I think, one of the big challenges of this forest component of the mission.
Thanks.
Okay, thank you, Kostas. We move on to the next presentation. And the next presentation will be, we'll stay on where Kostas left, on the ionosphere, and some validating global tech map by exploring biomass polarimetric measurements by Yunsu. So Yunsu, the floor is yours.
Yeah, thank you very much for your introduction. I'm Junsu Kim, working in Microwaves and Radar Institute in DLR. This presentation is about the validation of the ionosphere effect on p-band by validating the global TEC map against biomass Faraday rotation. This work is prepared by also with Felipe and Kostas, and also HR IOC team. So we first started with the ionospheric effects seen on biomass data. This is the carbon data we have seen the last slide of last presentation. I have two host and parasite images of the same time. You see some differences at the bottom. So at the second data, 19th, I made a sub-band, azimuth sub-band power ratio. Then it gives, it highlights the effect of the scintillation. So seeing the second column, we see stripes of the brightness and darkness alternates, and this direction will be continuously observed in following interferometric analysis. At the third column, we estimated the difference of Faraday rotation. They are scaled in within 3 degrees. We see an overall pattern of the change in red and blue, but still we see some it's oblique diagonal direction that passing through the differential Faraday rotation map. And the fourth column, the interferogram, we see again the fringes patterns are somewhat modulated by in this direction. And already in interferogram, we can see the, is there some pointer? Well, it's okay. At the very around 1/3 point from top, you see some horizontally moving part. It's like a sporadic E-layer thing. They already have effect on the interferogram because they are associated with the difference or change of spatial change of the ionosphere. They are seen on the interferometric phase, and going to the azimuth shift map, you have seen it already, so we pass it. And the range shift is compared to the azimuth shift very, very insensitive. However, we can still see some pattern on the strong noise, and its amount is 0.03 pixel, and it's around 1 meter. Comparing with the interferogram fringe numbers, and they are quite in good agreement. However, among these many effects, I in this presentation focus on the Faraday rotation, even not differential Faraday rotation, but Faraday rotation itself, because it is the only robust tool to measure the TEC, total electron contents, directly on single measurement. I go back slightly ago. So this is the archive of the global TEC estimation that dates back until 1998. For these almost three times of solar cycles, we can, here I plotted the daily global average in blue, and its monthly average in green, the orange, and the yearly average in green. We clearly see the 11 years of solar cycle, and seeing the seasonal monthly changes, we can see every year we see 2 peaks, which happens in equinoxes, not winter or summer. This change is most clearly seen in solar maximum. And in last year, since the biomass launched, we see a big dent of the TEC level, and it comes up during the equinoxes again. And this one is compared to our low-frequency star missions. JAXA has been operated L-band missions since long before, and recently, new missions have been started. Despite this long observation history, for example, JLS-1 has acquired this since before the archiving of TC map, or in low, the solar minimum, or recently the limited access to the data had been some problem, some limit for the global assessment of the Faraday rotation. Now the biomass and night stars are operating, so it is a good chance of comparing Faraday rotation level with TC. It was global average. Before globally averaged, the global TC map, ionospheric map is quite low resolution, 5 degree and 2.5 degree, and temporarily it has 2 hours of sampling rate. So on the right side, left side, we show some 4 days of the TC map changes. And on the right side, we try to compare the TC map global one and the Faraday TC estimated from Faraday rotation. The global extent, we see on the right, although I accumulated 34 successive ALOS-1 images, in global scale, it is very limited. If I don't see this white one, we cannot even identify these black lines. So it's globally, spatially quite limited. However, we zoom in, then we see that Faraday rotation can provide a very high resolution of TC estimate. So then how the Faraday rotation can be estimated and converted to TC is shortly described. The Faraday rotation is the phase difference of left, right, and right-left backscatter. So this angle is divided by 4 because of some geometric reason. Then how the linear basis is converted to circular basis is just multiplying this 1 basis transformation matrices. But here is on the left side and right side, the same matrices are multiplied instead of conjugate transpose is because the sense of the right and left is exchanged in the transmit and receiving condition. And then the estimation accuracy of the Faraday rotation is described by very well-known Kramer-Rao bound. Here, if we change the gamma with the well-known SNR to gamma relation, then it becomes more intuitive form of the multiplication of number of samples and SNR. When we apply here some various range of the number of looks and SNR, then we can see on the bottom right, so it's increasing the number of looks from blue to green, we can reach the Faraday rotation estimation accuracy from 0.003 or such a high level. And at the background, as for information, I plotted the distribution of the SNR, estimated real biomass data during the IOC. So yeah, SNR is on average 20 dB. It's quite high. And for Faraday rotation, not full power, but SNR to the right-left channel is required. So then, because we use only a portion of the backscatter, so its distribution is red, but still it is quite high. So we can expect quite good estimate of Faraday rotation. And this 0.03 degree of Faraday rotation converted to TEC at high latitude, it corresponds to 1 milli TCU. It is, I would dare say the insanely high accuracy. And then once Faraday rotation is estimated, then we need to convert it to TEC. But here we encounter more unknown. TC is merely the line integration of the free electron density from ground to sensor. However, what we measure the Faraday rotation is not only the density, but density weighted by the parallel component of the geomagnetic field to the propagation direction. Therefore, and because we don't know the vertical distribution of NE and also vertical shape of BK quite well, so we make a simple approximation to make these functions as the path simply some constant to make the Faraday rotation to be same. However, this uncertainty or unknown vertical electron content is not only the matter of the below the orbit to the ground, but also above is problem to be compared with the TC value, because the global TC map is measured by GNSS satellite, which is around 20 or 30,000 kilometers above, and above our low Earth orbit, around 700 kilometers slightly low, there are significant amount of the free electrons exist there. So then how much are above and how much are below? This is the question I would like to answer using the biomass data. So to do it, I sampled the biomass data every second of footprint. And every second I calculated one scattering, the covariance matrix. Where the two scenes are overlapped, then I took simply the average. Then for the geometric calculation, I calculated the ionospheric piercing point for different altitudes, and from each point I calculated also the geomagnetic field, later to convert the Faraday rotation to TC. And for the comparison, I sampled the TC from the global ionospheric map. For this one, during whole the commissioning phase, converted to the number of seconds, it's around 15 million seconds, and the sampled biomass sample is 186 million seconds. So we have, I think, large enough samples for analysis. This is one example of the calculated piercing point on the top left, and the geomagnetic field calculated there. We can see that at the northern hemisphere and southern hemisphere change of the sign and so on. And the interpolated TC is plotted at the bottom. This is from 1 day cycle, so it's 24 hours, but the Python gives the ticks for every 10,000 seconds, so it's not fit with the hours well, but still we see the periodic change that corresponds to the orbital evolution of the biomass. And these low TC levels are corresponding mainly on its path over Antarctic, and some higher TC values are when it goes observes at the higher parts, so mid and high latitude parts. Because I collected all of these covariance matrices, I can calculate the SNR globally and plotted them. So here we see along the tropical forest, where South America and Africa, we see relatively high SNR, where the forest reflects a strong signal, and at the Sahara or Middle Asia, it has relatively low SNR because backscatter is low. And in the Antarctic, as we have seen in the previous slide, it has some interesting structures, and this, for the details, will be presented by Patricia on Thursday. And now I corrected for Faraday rotations and tried to plot Pauli images. Here again, we see the bluish color over the forest, tropical forest along the equator, and low, so bluish and dark parts at the Sahara and Central Asia. And again, at the north part of taiga forest or boreal forest has some bluish, greenish colors, but the shade of color from tropical and boreal forest are slightly different. And there I calculated also alpha angle. Then here it shows the big dichotomy or some the volume scattering and the surface scattering. His volume scattering is green around 45 degrees and the surface scattering around blue. So now we go to the ionosphere. Here I compare the Faraday rotation TC and the global ionospheric map TC. On the left and right side, we can see on the left is slightly darker. But to make a comparison more quantitative, we come to the bottom graph. Then here the blue point is the sampled TC from global TC map. I will call it GIM TC, and the orange points are the converted from Faraday rotation. I call it Faraday rotation TC. We here see the orange points are, in most cases, slightly lower than the blue points. So to make a comprehensive comparison, this is only 1 day, and we have all the commissioning day phase. So this shows, again, the blue one is GMTC, and the orange points are Faraday rotation TC, so they are slightly lower always. Then how much they are? So on the bottom, it is the relative ratio is shown, and it's average around 71.1%. Around we can say around 70% of the ionosphere is below our biomass orbit. However, as you have seen, most of the samples are happening on the Antarctic. So it is better to make analysis depending on the latitude, and we know that the ionospheric physics is different from morning time and evening time. So we make a separation, then the result looks like this. In the evening time, we see the under-orbit ratio, to say, is around 0.8, around most of the low and middle latitude area, and polar region, it decreases slightly. And on contrary, on morning time, they are around 0.6, and in polar region shows some deviation. So why it is so? So this is the first explanation that will be later compared with the ionospheric model, EDA, or so on. So in the morning time, the evening time, because of solar radiation has created a very strong peak under the star orbit where most of the atmospheres are concentrated. Therefore, the ratio of the under orbit is relatively high, while in the morning, yet the peak is not well developed. Therefore, the relatively smaller part of the ionosphere or free electrons are existing under the biomass orbit. And again, we analyzed in the monthly changes. In the descending orbit, they are somewhat well-defined. At the polar latitude, they are small, but in the mid and low latitude, they are increasing. And the peak ratio is observed during August, while the other months is low and high and come down. And in the ascending, in the morning time, it has some not well defined, but if we ignore the June acquisition, then in July, we have a higher ratio in the northern hemisphere, while it changes in the following 3 months, and in autumn, the higher ratio appears on the southern hemisphere. I think it's somewhat related with seasonal change and the solar illumination thing, but morning is before the sunrise, so we have to, again, further analysis required. And finally, the high resolution aspect of the biomass TC is shown. This is one selected passage or tangent over Antarctic, around 4,000 kilometers. And on the right, again, blue is from the interpolation of GIMTC, and the orange one is from the Faraday rotation. And we see always we have much higher resolution and fine scale structures in the ionosphere, because we have many. So there are sometimes, for example, June 18th, they have some similar trend, while in the next third day, the TC estimation from the global map is too high, or in July 3rd, we have some undetected high concentration of TC and so on. So this is very early estimate using the IOC commissioning phase data, so we need to further analysis and some potential scientific results that can be transferred to the space weather people, because the orbit altitude of LEOs are around 609 kilometers, is for them has no meaning at all. So therefore, they didn't do anything for their particular electron density profile development and so on. But I think our research can provide them some extra information and other things. Thank you very much.
Thank you, Yunsu. Any question, Yunsu? Yes, Sean, please. Microphone is coming. Yes.
John's in this ratio of above orbit and below orbit, did you notice significant differences between high latitudes and low latitudes? Because you'd expect there to be.
Yes, I also expected some change to happen rather in the mid latitude and low latitude and mid latitude have some strong differences, but yeah, at least for the IOC period, mid and low latitude have some similar pattern, and polar regions are different. Of course, yeah, this is also somewhat different from what I expected, but yeah, but not very, how to say, contradicting with our knowledge, so I plotted them and shown here.
Okay, thanks.
Okay, thank you, Yunsu. Then move to our next speaker. Thank you.
Thank you very much.
Our next speaker is again Stefano De Baldini. He has been a very important figure throughout the years, and very glad we have him here.
Thank you very much, Michael. So good morning again. So here is a talk on the role of ionospheric layering. So as Kostas said, we have evidences that the ionosphere is a layered medium. This was not very much considered in the past in the context of synthetic aperture radar processing, but with biomass we do have to put this on the table. So, and why? Well, I like to recall that biomass is an interferometric mission because a lot of its most important products are generated by interferometry. HBD is done with ground-notched products, so by mixing two different acquisitions coherently, forest height, disturbance, tomography, ice structure, motion, all of those products are done by coherently processing different acquisitions. So it's very important that we know how to handle any phase difference. And due to the large sensitivity of P-band to TEC, the ionospheric phase advance is by far the dominant source of degradation for the quality of interferometric data. Just take a look. One tech unit at P-band gives you 40 radians. So if you have a variation of one tech unit, then you have like as many fringes as you like, basically. And just to recall the major effects of ionosphere on interferometry, you have phases. So up there you see topographic fringes, and then you see on the left part the two fringes that are due to ionospheric propagation. You have range and azimuth shift. This is an example of coherence losses due to the ionosphere, let's say, creating a displacement of the position where the target appears. In this case, it is not much of a problem because you can do a data-based co-registration, and so everything works beautifully after that. But there are cases where the ionosphere is so angry and it changes so fast within a synthetic aperture that it's not just mispositioning, it's also defocusing. And when you have defocusing, it means that two different images are defocused in different ways. So co-registration is simply not enough in this case. You need to refocus. And so the scope of this work is to understand how to model the ionospheric signal, how to estimate it, and how to correct for it. Now, I am going to use multi-squint interferometry, so I prepared this slide so for those who are not familiar with that. What is multi-squint interferometry? Basically, with the SAR, so any SAR allows you to focus with a particular squint angle, and you can do this in post-processing. So when you have a data, you can always reprocess it to, let's say, to change the system line of sight along different squint angles. So you can look with a variation of a couple of degrees in the case of biomass. We do this in both passes so that we can analyze the variation of the interferometric phase with the squint angle, as in this picture. And so what happens if you have multiple ionospheric layers? Well, it basically means that each time your line of sight crosses one layer, it accumulates a phase advance. And of course, this is a function of the height of the layer. So basically, if we analyze this variation, then we can, at least theoretically, we can understand the height of a layer and also understand how many layers we have. Just to understand how it appears, this is synthetic data, just to show you that in the case of the ionosphere, if you visualize this phase in the azimuth and squint plane, then you should see a slope. If you only have the geophysical phase, so the phase of the target, then it appears as vertical bands. In the case where you have everything, it's mixed. It's also interesting if you pass in the Fourier domain, by which I mean that I just do a 2D Fourier transform of those figures. In this case, we have that the ionosphere should appear as a line, as a blade, we say in Italian, with a certain slope. If you only have the target phase, it appears as a line with no slope, and of course mixed. Then you have all the possibilities. Now, some data. Here we have a 3-pass descending stack over Amazonia, more or less the border between Brazil and Colombia. The height of ambiguity in this case is very, very large, so we don't expect any topographic fringe here. And this is what we have. You see the phase with some fringes, which are due to ionospheric propagation. Coherence, this is the same panel I showed before, and so we have coherence losses due to azimuth shift, mostly. Here we have the range shift and the azimuth shift. You see that they match very, very, very well. And indeed, we can do a database co-registration, and it works beautifully. So in this case, coherence is, so we can apply the traditional INSAR processing, so the traditional paradigm to do a database co-registration, and then if you like also to remove a phase plane, and everything works beautifully. So this is a good case, let's say. Here is how the multi-squint phase appears. So you have azimuth and squint. You see these characteristic slopes, which means that the phase that we saw was due to the ionosphere. And in this case, it was consistent with a layer at the distance of some 300 kilometers from the surface. But now let's change place. We go in Antarctica, in inner Antarctica. Again, we have an interferogram with a very large height of ambiguity, so we don't expect any effect on the phase due to topography or to penetration because of the very, very short baseline. We don't expect any motion here because at 3 days in this part of Antarctica, it is not, we don't have any deformation ongoing. And this is what we have. So the interferogram, as it is, before doing any processing, and you see that we have a lot of fringes, which are for sure due to ionosphere, and also very severe coherence losses. The azimuth shifts are in excess of 100 meters in this case. So let's try to co-register. It doesn't work. So in this case, we have the ionosphere is so angry with us for some reason that it creates defocusing. And the defocusing is different in the two takes. So co-registration is simply not enough. Let's take a look at the multi-squint phase. It's coherent now. So basically, since to generate the different squints, we also need to reduce the resolution. In this case, the azimuth resolution is on the order of 300 meters. Well, the focusing at this scale is not so important. And so we see that if we work with lower resolution data, then we can retrieve coherence. And this is a clear indication that all the coherence losses that we saw were only due to ionospheric propagation. This is it. If you take a look at the phase, you see that it's very, well, it's very complex with different slopes. And indeed, if we take the Fourier transform of the multi-squint phase, this is what we have. We say that an ionospheric phase converts into a line with some slopes. In this case, we have this sort of butterfly. So we have many slopes, which means that we are dealing with a stratified ionosphere. If you like, yes, we can also do something more and do ionosphere tomography. So this would be a 3D representation or a section of the ionosphere. Let me say that the processing is absolutely not straightforward here. So this is just a suggestion, and this is a work in progress. But I want to speak about how to estimate and correct this ionosphere. What we wanted to do is, so it was clear that we need a new paradigm. The old paradigm to co-register and remove a phase plane is not valid for most acquisitions of biomass at boreal or Antarctic latitudes. So we need to find out an algorithm to estimate the ionosphere and to correct the data. We also would like this algorithm to be transparent, meaning that if we happen to apply it in a case where it is not needed, it shouldn't hurt. Now, I will be very, very fast here. Sorry, there is no time to go into the detail. Just to say that the observable for us is the multi-squint coherence. So we work on complex coherences, and we process them with this inversion algorithm to estimate the ionosphere at the different layers. So the outcome is a set of layers that represent the ionospheric phase. It is an iterative algorithm with, fortunately, seems to converge easily. And it also has a null space, meaning that the solution is not unique. I will discuss on this point. Now, how do we correct? The ideal process would be to defocus and refocus using a time domain approach, so that for each ray you can account for the ionosphere along that ray. That would be very intensive on the computational side. So what we do, basically, we split the data into subbands, such that if you resum all the subbands, you get back to the original data. And so the correction algorithm is just to correct each subband individually. So it's, let's say, it's not hyper clean, but for biomass, we are within the boundary where it works fine. Now, this is an important slide. We say that if you, in the spectral domain, in the Fourier domain, so this is the azimuth frequency and the squint frequency, the ionosphere appears as a layer, as a line with a certain slope. This is true if you had an infinite resolution, but resolution is finite because your aperture is finite. We have an aperture of a couple of degrees. So the two lines become fat lines, become rectangles. And so what is the sensitivity of biomass interferometry to layering? Well, let's say that in this region, one or two layers doesn't change your life, because you don't have the capability to resolve them. In this other region, they do. Now, this region corresponds to high spatial frequencies. So basically, this means that as long as the ionosphere is smooth, so it doesn't change too rapidly in space, we are not too sensitive to its height. We are not too sensitive to how many layers there are physically. Maybe one layer with an approximate height can do it all and can compensate your data beautifully. But if the ionosphere is going faster, So if it exhibits rapid variations, then we are sensitive to it. And in this case, we need to account for different layers, and we need to know their height too. So it's a multi-scale problem. And now, back to the data. This is the same. This is again Amazonia, where the ionosphere is mild, so the co-registration works beautifully here. And indeed, you have on the left phase and coherence with database co-registration, and phase and coherence with our algorithm. So I would say that they are equivalent in this case. Just to let you notice, this is a river basin which exhibit a spectacular phase change across the 6 days. Now, I don't know too much what it is, but it is surely connected to water. So it's probably a flood or a big change in the water content. We have here an example again in Amazonia, this time with a long baseline. I mean, with a baseline that we can compare to the one in the Tomo phase. We have a height of ambiguity of 70 meters and topography. So in this case, we would expect topographic fringes. On the left, co-registration and removal of a phase plane. It works nice, but there are some residual fringes. On the right, with this correction procedure, in this case, we just see the topographic fringes, which means that the processing is working fine. Australia, this is where we have the BCT in New Norcia. And again, on your left, co-registration, so phase and coherence, and on your right with this correction method. You see that co-registration in this case is simply not enough. You cannot recover coherence by simply co-registering. The data with this correction, which does a refocusing, it seems to work. We are not cleaning the phase. So the algorithm is not perfect for what concerns the phase correction. And why? Because of the null space. We are not too sensitive to smooth variation. So in this case, the algorithm is not capable to say if those fringes are due to the ionosphere or to something else. This is a limit. Antarctica, this is nice because here we have the multi-squint phase with a different slope, and this is the residual, so the difference between the observed multi-squint phase and the one that we try to model with the algorithm. With one ionospheric layer, there's no way to reproduce that structure, and indeed we have a residual. In this case, we need to increase the number of layers to be able to reproduce this. And at the end, this will be a correction with 8 layers. This is where we are. So on the left, again, co-registration. On the right, the correction algorithm. Again, this particular data set is supposed to be perfectly coherent. And indeed, after you remove the ionosphere, it is. Again, those are residual phases when we are blind to them. And then, since I'm a bit late, just let me show you a data set at boreal latitudes. Here we are in northern Russia. Again, we need a multi-layer correction to pass from the interferogram on your left to the interferogram on your right. So, to summarize, Amazonia seems to be not too difficult. We can correct for ionosphere in a relatively simple manner. If we want to go at boreal or Antarctic latitudes, this is not the case. And in this case, we really need a multi-layer correction, and we need to use heavy weapons. The main issue, so let's say that at the point where we are now, we are confident that we can recover coherence. So coherence losses are no longer a problem. We can cope with that. The problem now, and you can notice that this is a work in progress, is that we have residual fringes that have at large scale. And this is because multi-squint is not sensitive to large-scale effects. There's no way out without a reliable prior, and reliable prior can come from mixing this with Faraday rotation or range dispersion, or maybe using external model. This is something that we will see in the next month. Thank you very much.
Are there any questions?
Yeah, okay. Thibaut? Yeah.
Hi, thanks for the very nice presentation. Can you, do you have a way to estimate the number of layers in advance?
Yeah, we do it in a very simple way, basically.
The same question. Yes.
This is the multi-squint phase. We start with a single layer and take a look at the residual. If we are happy, we stop. If we are not happy, we go on and add another layer.
So when do you decide when you're happy?
There is a threshold, and which I do not remember, but let's say we have a metric for quantifying how flat the phase is, and when it's sufficiently flat, we decide that we stop.
Excellent. Follow-up question. So here the model estimates just the number of layers, but not their, let's say, spatial...
and their height, of course.
Yes, how can I say? They are uniformly spaced? It doesn't matter if they are uniformly spaced or they can be randomly spaced?
No, actually, let's say, if you have physically a single layer that goes up and down, then we model this as many layers. Yeah.
Okay, thanks.
It's easier. It seems crazy, but it is easier.
I have one question. Stefano, how do you see that for, how would you deal with that in the routine data processing, in the routine phase?
So let's say that we have, so the processor is in place as a prototype. Aresis is implementing the processor as a real processor fit for routine operations. We have, let's say, there is a point in the processing line where we sort of predict in a quick and dirty manner what the performance of the new algorithm would be like. And there we decide if we stick with the old processing line or if we need to go to the new processing line.
And it can be automated?
Yeah, yes.
Okay.
I have just one question. Does it matter if you know what layer belongs to what acquisition? And when you do the correction, let's say you fix the master and you correct the slave, is there any effect if there is no knowledge on that?
No, that would be beautiful to do. Actually, at this point in time, we don't do it. So we just correct the slave, which means that maybe we are over-correcting the slaves. So let's say we are defocusing the slave in the same way as the master is. It would be beautiful to be able to from Faraday rotation, we could get this information. So yes, we need to embed this in the processing.
But still, you can correct the data quite well. So if there is an effect on this not knowing that.
Say it again.
I don't know if there is an effect of not knowing that, because at the end it seems that you are recovering the phase and the coherence. So maybe.
Yes. But it would be nice to separate. Thanks.
Okay, we have to move on. Thank you, Stefano. Felipe, you can already move to the stage. So the next talk will be staying again on the ionosphere. So it's a heavy topic for today, but also I think also for the mission itself. So the floor is yours, Felipe.
Yeah, thank you. Thank you for the introduction and thank you for being here. The results that I'm going to show now are the outcome of a lot of discussions that I had with all these people involved, because the ionosphere correction is something that we need for further processing of the data. So we already know what biomass is, so I'm going to jump directly to one of the applications. So let's say we have biomass looking at some target, let's say some trees. Since the wavelength is very long, we can penetrate all the way to the ground, and then when we have another pass, we can start using the phase to do some interferometry. If you have some more passes, you can start doing tomography. The goal of it will be, for example, estimate this kind of vertical reflectivity profiles to see what is the structure of the forest. To do that, you need the phase to be clean and the coherence to be clean. In our case, since we are at a very long wavelength, then we are affected by the ionosphere. Yeah, now it comes. That will add some phase screens and the correlation. That means it will change what we see or how we interpret interferometry, and it will introduce also some azimuth shifts that Stefan already introduced, but we're going to talk about them again. So it was actually good that Stefan did a good introduction of the effects before. What we want to do is to come up with some different ways to try to correct for all these effects, at least in the interferometry at first. So in this presentation, I'm going to talk about azimuth shifts and multi-squint again. I'm going to propose a way to combine them for these a bit of more challenging scenarios. Going to talk a bit about a polarimetric optimization that we thought is a good way to come to optimize this correction. And it's something that is a bit off topic, but I wanted to show at least one slide. It's something that I was working for some years during my PhD. To try to correct single images, because with interferometry, okay, you fix the interferogram, but you don't fix the single images themselves. And then with this autofocus, sometimes you can get to something better. So this is the scenario that we got. We got biomass illuminated some targets. Let's say these trees over here. We have the ionosphere in between that will add some phase to the targets. And on top of that, the integral of what you see across synthetic aperture might, when you look at the interferometry, shift one of the targets. And that shift can be directly related to the slope or the first derivative of the phase that you're seeing. You can correct that by blockwise cross-correlation, as it was presented before. The problem is that the performance is scene-dependent. So if your scene is a bit, I don't know, you have some man-made structures or some periodicity, that might be affected. One of the problems here is that whatever you measure, it can be contaminated by previous co-registration errors. So if you have errors in the co-registration, you might bring them along with your when you integrate. Another way to look at it is next. Okay, look at solving it with multi-squint, where you do azimuth sublooks. That is as if you are looking at different parts of the synthetic aperture, and then you do one minus the other, and again you go back to the first derivative of the phase that you want to integrate. The good thing of it is that it only sees ionosphere, so it shouldn't be sensitive to co-registration errors, and it's dependent on the coherence. So what they both have in common is that they both measure first derivatives. They both require integrations. We have problems where you don't have you don't know the constants of integrations, and you have random walks. But by focusing and defocusing, you can correct both things at the same time. So we have some kind of redundancy because you can look at the same problem by two different angles. So for azimuth shifts, what I do is I take the two images, I do blockwise cross-correlation to get a 2D map of the first derivative, which I will integrate, correct, and do that a couple of times. For the integration, I'm going for a least mean squares integrator, because I can express the derivative as as a linear operation, and I can assume that the errors in the estimation of the shifts can be Gaussian noise. To try to make it more robust, I can use all the information that I have, all polarizations, because the premise is that the phase affects all polarizations the same. So what you have is redundant information. So why not using it to make your integrator more robust? So that is, again, the Gabon scenario that we were showing before. And in this case, between two passes, I have some interferometric phase, and I go and estimate the azimuth shifts, and I say, okay, this looks like the first derivative of the interferometric phase, so that looks good. I go integrate it, and I obtain what will be the first, like a low pass version of the phase that I want to correct. It is low pass because the integrated operator is by itself a low pass filter. And on top of that, I have a lot of averaging when I'm doing the block processing, because I have the block averaging, and you just like sampled versions of what you want to estimate. I correct that a couple of times because it's a low pass solution. Then I have to apply a couple of iterations. But in this case, that it went for a bit of a challenging one, I'm getting to some constant in azimuth shifts that I can interpret as a residual trend, a residual linear trend that I'm not able to integrate. I interpret is because I don't know, I might have some random walks, or because I don't know the constants of integration. Anyways, so here I have an example of what I expect the ionospheric phase to be. I go and look at the interferograms, and they look a bit better. I also see that I recover a bit of coherence. So in these maps, the green is good, but I still have some residual phase that I will have to deal afterwards. Again, if you have a constant azimuth shift, it's as if you have like a constant multi-squint. So I haven't solved the problem yet, but I'm looking at it from two different angles. Then if I go for multi-squint, again, so you do like sublooks, and then you do the interferogram, and then you do the interferogram of the interferogram to obtain the multi-squint phase. I will have to integrate it and correct again. Again, I use a least mean squares integrator, where I try to combine all redundant information I have. And I obtain this kind of multi-squint phase that in principle, it should be like a higher resolution version of what you get with the azimuth shifts, because you're not doing all this block averaging and sampling. But still, I get to similar results. So I kind of go back to where I started. Again, you see that I recover some coherence, I recover some phase, but I still have some constant in the azimuth shift. So what I propose to do, at least for this more complex scenario, is to do a two-step solution where I go and first I do the multi-squint phase, I correct it, then I go and estimate the low pass residual with the azimuth shifts. I do it a couple of times until I get to the scenario where I have no multi-squint and no azimuth shift, so that's good. But I still have some residual phase that I cannot get rid of. So even though I recovered the coherence, so then what we thought is that I interpret this as missing constants of integration, or you can look at it as, okay, the ionosphere is changing so slow that doesn't change much inside the synthetic aperture, so it will be safe to try to remove it directly from the data. Then just to not remove the information that I want to keep, which is like what I call the phase of the trees, I decided, okay, let's just do a look at the subblock interferograms and then remove a low pass version of that. And like this, I get a phase that I can work with. So this looks kind of good because you have like zeros in the surfaces, you have some phase where you have trees, and I recover a lot of the coherence. So before moving forward, so what we thought is that, okay, why don't we try to do polarimetric optimization so that each pixel of the image can be the best version of itself. And to do that, I kind of project every pixel into what will be its best polarization because I want to work with interferograms which are clean, which don't have a lot of noise, because every noise that, if you have a noise in the images, when you integrate them, you're gonna be carrying random walks, so you don't want that. I go and check what will be the variance of the local variance of the optimized interferograms, and I compare that with the local variance of the interferograms of the single images. And here I see that, okay, red is bad, so the optimized interferogram is better than all other interferograms alone by themselves. So that is good news. And that's more or less what I was expecting. And then I go and compare what happens if I integrate just one interferogram, a combination of all four, or just taking the optimal. And the last two cases give me similar results. So when you are combining redundant information, you're just averaging. So at the end, I think it's safe to say that both methods will work, even though in this case, I will say the optimized polarization works a bit better, but yeah, it's something that maybe is good to keep in mind. I don't know how I'm going with time, but before just closing, I wanted to show something, because the thing is that I was saying before, when you go and correct for the interferometry, so you're fixing the interferogram, but you're not fixing the images. So what I was working for some time was in this prototype of an autofocus where you can estimate not the differential, but the absolute phase and correct it in every image. Here you can see that, okay, I was able to correct more or less. So if you have colors, you have the focusing, and eventually I recover some of the focusing, I recover some coherency. I estimate a single pass ionosphere. One of the reasons why I put this aside is because, at least in the context of biomass, I found that it doesn't really apply everywhere. So if you have ice, which is very homogeneous, you don't have much contrast, you can't really apply it. And also when you have forested scenarios, it's not really good. So this is also, again, close to the VCT. So you have some crops, so the contrast is very good. So there you can apply. But maybe with the knowledge that we got now, I can go back to it and take it out of the drawer. So yeah, these were my notes. And then just to close, we propose some methods to try to correct the ionospheric contribution in the interferometric phase and recover the coherence, so that when we go and do the tomography is clean. I recommend to do a combination of both. Also, again, if even in an easier scenario, just one of the methods will work, it doesn't harm to just do both. We think we can just remove this low pass component. I don't know if in any operational scenario, but at least for this forest we can do it. And yeah, then I compare the use of multiple polarization of the optimal, and it's something that is good to have in mind. And yeah, we just keep validating in our data sets to see if we can bring this forward to a more operational state. And that's it.
Thank you. Yeah, yes, we still have plenty of time left, so there's definitely time for questions. So yes, see you. Yes, Stefano, then yours.
So thanks a lot. My question is rather technical. When you integrate your the difference of the multi-squint phase, or where you integrate the azimuth shift, you need to ensure consistency across different range lines. How do you do that in practice?
When I design my integrator, I design a 2D integrator. I force that the solution that I get is consistent also in range. And I do that also by forcing some tight points at the beginning and at the end of the image, so that each random walk or each integration constant will not make my integrator go like in all possible directions. So I kind of tight the solution. I force it to be consistent in range.
Okay, thanks. And one very quick, I miss it. How do you correct? You do the semi-focusing?
Yeah.
Okay, thanks.
Yes.
I have a somewhat related question here.
Yeah.
So you use with split beam techniques, and so the tedious thing is this integration step and determining the integration constant. Did you also try split spectrum techniques?
No, I didn't because yeah, the spectrum here is very small. I think at some point I tried with some older data set, but didn't really get me to where I wanted. Yeah, I was more focusing to try to correct the single images, but yeah, still not.
The spectrum is narrow, but the frequency is low, so the factors that you need are similar to L-band satellites. I will show in the afternoon, it works quite well. And so if it works, I think it's much more straightforward than the method with the subband in the azimuth spectrum.
Yes, I mean, I think it's maybe a matter of trying with this data set. I remember I tried with some older data set and it didn't give me nice results, but maybe in this data set can be helpful.
Yeah.
And we have some other data.
Oh, yeah. Actually, same question on this, but maybe I can rephrase it again. If I'm not wrong, Biomass has very narrow bandwidths, 6 megahertz somethings, and do you see this can make some challenge when you're extracting the sublooks or subbands?
If you do range sublooks, yes, but if you do azimuth sublooks, not necessarily because the band is different. And we still have this. I don't know. I always remember just the angle. So some 3 degrees angle, but when you project into the ionosphere, there is a lot of variation between one sublook to the other.
Okay. Thank you. Thanks for.
Okay, thank you. So I don't see any other questions. So thank you, Felipe. So then we move to the last speaker before the lunch break. Will be provided by Din Automing on and now moving away again from the ionosphere and going back to the surface. So he will bring us to P-band radar stability and tomographic mapping of the Amazon. So please, Din, the floor is yours.
Thank you, Jacques, for introduction. Good morning, everyone, from my side. How are you today? So I think that we are a little bit more technical in the anisotropy correction. Here I try to go back a little bit to make something less technical, like COSTAT did at the beginning. So in this talk, I together with my colleagues from Mother of Biomass, Madame Tuyleton, and with my colleagues from LIS and from Tomosa. So basically that we're going to share with you how stable up the B-band radar signal, how stable it is. And then I really proud to share with you the first ever tomographic data from space. Okay, so let's talk a little bit about the physics. So basically that's in the top on your left, so that's what we usually have with the C-band. So basically with the wavelength, something like 5.6 centimeter, you will never get something coherent, something stable in the forest. And that's why we never did something in the forest with the C-band. And then that's why we think about how exactly we can do for the forest, and then the only way to do is to go to low frequency. So we go to the L-band and we go to the B-band nowadays. So in the middle, you can see that with the B-band, we have the wavelength something like 69 centimeter, something like this one with respect to this one, and we see the very strong coherence as a function of time. For example, here is the data in the middle of the top. You see here it in during the Gavan. So basically, that the baseline, the distance between the two acquisition time is just about almost zero baseline. So we don't have anything with the geometry decorrelation. We just had the temporal decorrelation here, and we see with the tree time, we see the mean coherence is something like 0.85 with respect to the sentence 1 is about something like 0.28. So we gain something like 0.57 again in coherence, and that's really, really good for us because at the beginning of the day we think a lot about how exactly stable it is. Can we do something like coherent processing for the forest? And it's good news for us. So, and then let's keep moving. Okay, so when we're happy with the stable it is, we take about the time data to do processing. So when I take pick up the data, it's not so many choice for me because the data at that moment is not available everywhere. So I take the best scenario we can do. We take something like 6 image here. So in the forest or the forest in Kalimantan, so basically that 20 years ago there's almost natural forest here, but now there's a mix, the landscape is mixed between the primary forest and also with the oil palm plantation. So, but basically we have some idea about what exactly the forest structure over there. Okay, so because at that time we don't have the level 1C, so we had to do a little bit exercise from the level 1A, so we had to do a little exercise. So the idea is we want to reconstruct the 3-dimension of image in the forest. So to do that, we try to revisit the same site, a slightly different angle, and then we try to revisit again. So what we do is we try to do something like computerized tomography for human eye, but basically that for the forest we cannot print the forest in the computer or in the Hobbiton. It's not no way to do that. We just do something like a couple of degree angle here, with respect to 360 degree in the Hobbiton. But even that we can do something. We can do something like, from that one we expect to try to decompose in the multi-layer in the forest. So to do that, before that one we had to do some a little bit exercise. So we have several images as a function of time. So and then we had to try to correlate everything together in a certain preference. For example, we select the preference in the December of 23 here. So as we mentioned before, like we see in a lot of talk about how the correlation based on the database will be failed if there is a strong atmospheric contribution. But fortunately here we don't see very strong atmospheric here. Of course, there's a little bit, but not very strong, and the coherence is very, and the interferogram is very clean here. So we are really super happy to see how colorful it is of the interferogram here. So the fringe is very clean, and we see how the function, how the phase is changing at the function of the baseline here. So, and then moving on, is that enough? Okay, so basically that the idea is when we do the correlation, we subtract for the blast phase, we subtract for the phase related to tomography, and then whatever we can do. So basically that because our satellite is something like 666 kilometers above Earth. So when it transmits, so it has to propagate in the atmosphere. So and then we subtract some phase, some plus phase, some tomographic phase. There's some residue phase that we have to deal with that one. And the second one is because we want to work in the vertical, and in the high we had to have a good reference. So basically that people using work on the respect to the mean sea level high, or even with the kind of ellipsoid. Here we want to stick our reference in the ground surface level. So basically that we try to use as a reference of Eurometer, we stick to the ground surface. And then to do that one, we have to think about how to do that. Basically, that we try to do that. We have to try to think about from the radar to the target. So there is an optical bus. We try to estimate the optical bus, and then we use that one to remove down the data. So to do that one, we think that this one will be related to something like the phase. So the distance between the radar and target or the ground, that is the distance. And in the radar, with no way to measure the distance, we just correlate it to the phase. It means that to do phase calibration, he will estimate, we try to estimate the phase which correlated to the ground contribution. We call it the ground log phase. So to do that one, we try to estimate the big matrix, like this one you see here on the top, on your right hand. So basically that we combine for polarimetry and interferometry. So basically that for the first component we see, for here we have 1, 2, 3 for 6 by 6 for interferometry and 3 by 3 for polarimetry. So we combine together, and then what we try to exploit the diversity of polarimetry to see where is the ground. And to do that, basically that we try to do singular value decomposition and to find out the maximum and the second maximum to reconstruct based on a certain sum of Kronecker products. We use just sum of Kronecker products, and then we try to synthesize, to associate with the crowd and with the volume, and then we try to isolate the crowd only, and then we just fit on the structure matrix of the ground, and we retrieve the phase, and we get the phase hourly contribution here, and then we using that phase to subtract it in the signal we have, and then in this case, the phase of the data will be well calibrated. And whenever we done that one, everything will be easy. In this case, we have something like multi-acquisition here. We can use in something like Fourier transform to transform our data from the multi-acquisition to multi-layer of the data sets. So basically, that we will have a single look complex, but in the different layer, and with respect to geometry. So one way to see tomography is we to take a slide, a profile like this one. So I'm happy to show you that is the first ever tomography profile you can see here. So on the top, so basically that you can see in the azimuth being something like around 2000. You see the forest over there. So basically you can see there is a quite strong contribution is visible in the crowd with respect to not only the core-bone also, but also the cross-bone. And for the volume scattering, we can see that there is some high interaction in the volume layer in the cross-bone. And the interesting is I can take your attention in the azimuth up 7,000. So you see in the 7,000, there is an open space, and you see there is the B-band can even go inside subsurface. So basically, that's we see something is under the surface. So it's interesting for me because that is the first time I see that one. So the key idea is we see the phenomena very, very similar to what we found from long time ago from the airborne combined data, from the tropism, from the ARISA, and so on. So we are happy with that tomogram. And then what can we do? So what is the next? So our primary objective is about the biomass, and we think about how to exploit the tomography for biomass. And because with tomography, we can slide the forest layer by layer. So basically, because of the Fourier transform here, so we can have a multi-layer here. So on the top, so for example, you see how exactly the forest close to the ground and above the ground, something like 50 meters with different polarimetry for the core-bone and cross-bone here. So basically, that if we go a little bit above the ground, we can able to cancel out the ground echo, and also the intensity here is something like amplified by the height with respect to the ground. So it means that with the tomography, we learn learn the way how to get rid of the ground contribution, because the tomography, there are some and so phenomena that we not really expect, that really related to the phenomena that we want to retrieve from the forest. And for example, that we take that knowledge to apply for what we interested in is the biomass. For example, on your lab, it's a classic optical image about the whole scenes of the biomass, something like 60 kilometer in range and 140 kilometer in azimuth. And in the side beside the optical one is a poly composite of the image, and we see the phenomena is with respect to the optical is extraordinary. It's much more information to appreciate. And then and then we have something like the slide, the tomography slide horizontal at 30 meter. So here a little bit, I explain a little bit here. So basically that we have something like 6 megahertz in range. It means that's the optimal value we can get for vertical resolution from the biomass is something like 20-25 meter in vertical. That is the best we can get. So basically, that when we're talking about the layer at 30 meter, it will be in general include the main contribution from about 20 meter to 40 meter. That's the main contribution, but also we have to take into account the power loss from even from the 5 meter or 10 meter of the forest. So In the bus, we take that layer 30 meter, we combine with the phase center. So basically, where is the volume, where the bit in the profile, the center of the bit, and we take two information to account together because layer 30 meter is usually good for the high random biomass, and the phase center of the canopy is really good for the low random biomass. So we combine together. So we exactly the same law we learn from the airborne combined data, and we retrieve that biomass information here. So we're quite happy because why? Because that's what we are expectation. Because if we go into the big swarm forest like this one, we expect the biomass is something like about 250 to 300, something this one, and it's as expected for our expectation for the biomass. And we are really happy with this one. So from my side, it's okay. So there's just some summary. So stability. So we are really, really happy that the biomass, the B-band radar is really stable. So and then the second thing is we really also very surprised is we almost replicate every finding. Every discover what we learned from the airborne campaign, we can replicate it in the biomass mission. And to make it happen, the phase calibration is important because otherwise that you will see some defocus in the vertical resolution for the image. And our further results is encouraging. So thank you a lot to ESA for making B-band available in Spain. So as a next step like this one, so feel free to explore. So that's all from my side. Thank you for your time.
Thank you, Dean, for your presentation. Thanks for staying well in time. There's time for questions. Stefano, please.
Thanks a lot, Dean. A comment on the size of the window that you use for tomography and for estimating forest biomass density.
The size for tomography processing here, that's what you mean?
Yeah, the size of the window.
The size of the window here is single look complex data.
Yeah, so but to do the SKP, you need to average, no?
Right, for the SKP for phase calibration.
That window.
Yeah, okay. For phase calibration, we take something like we take in the RAN, we take something like 10 look in the RAN, and in azimuth we take something like 30 in azimuth and 10 in RAN. So okay, basically so that's we
200. So it's 200 meters in range, then 10. Yeah.
So 10 is something like 200, right?
Okay.
Right.
And for estimating forest biomass, it is the same window, or
the same window? No, okay. For estimate biomass, we're using exactly the full resolution here. So basically, that we estimate the full single look complex, but in a different height. So we
it's single look.
Single look.
Okay.
So basically, that if we record it in ground range, so we have something like 15 by 15 meter biomass.
Okay.
Wow.
Thanks.
Yes, one more question there.
Thank you, Dean. About tomography, did you use the Campon or the Fourier method in these results?
We write very clear here that the beamforming, so basically that we detect the data, we take the Fourier transform, just beamforming.
Okay. Can you go to the previous one in which you see the tomograms? Okay.
Yeah, this one also the beamforming here.
Okay, they're so clean without side lobes, it looks like Campon. Okay.
Yeah. So
just
even
in case.
So even it's a surprise for me, but I say because I expect that I have to something like going to Carbon, or going to music, or even going to deep learn to improve the quality of the tomogram. But it's done.
Yeah. Okay. Just in case for the users, Campon is also a very well-known algorithm, but it is radiometrically non-linear. So in this case, for the best scattering maps, different levels maybe for.
Because it's a radiometry occurrence.
Yeah. Thank you.
Why? Because we have a very systematic baseline in space. so we can do Fourier transform easily.
Okay, because the baselines are optimal. Right. This is why Fourier is good. Yeah.
Exactly.
Thank you. Thank you.
Thank you, Isa.
Okay, thank you, Din, for sharing sharing those first results with us. So, and with this last talk, we conclude the session. So there will be lunch now, and we'll be reconvene at 2:10. So there's one announcement for maybe the room, right?
Yes.
Okay.
First thing, we will take a photo now, a group photo on the stairs. So please don't escape. Let's just meet on the stairs. And then the second thing, after lunch, for the last session, we will meet in the other room, because here it's a bit, we are many people, so maybe the other room is better. So after the break, we meet in the red hall.
Okay,
Thank you.
Upstairs. Yeah. Thank you, Din, and all the speakers of this session. Thank you.
Can you please move out to the stairs? We want to take a photo. Very important, huh? Especially Tui, Sean, Michael, we need you in the first row, huh?
And Björn.
And Björn, of course. No, you have this nice shirt, so you have to be...
AA check, AA test. AA check, AA test test, AAA check. AA check, 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 AA test, AA check, AA, AA.
Yes, I arrived with plenty of time, so we haven't much face to face. No, just emails.
Very nice to meet you. Sorry for shuffling because
No
we have
problem.
shuffling.
No problem. I think Friday many people will be gone, so
Yes, exactly.
and myself included. Are you presenting the session?
Yes. You're staying over here? Huh? You're staying here now? No. Just make sure that I take my... No, I'm staying here, yes. I am the keeper. Well, yes. Si può caricare la presentazione? Eccolo Claudio, proprio lui. È vero. No, non è vero, perché non appoggiò ma l'hai scritto tu il proposto?
Sì, ho fatto, non ho più messo di metà giornata.
Ah, non lo so, perché io vedo ci vuole. Sì, sì, diretta interrotta. Allora, vabbè, dobbiamo vedere se gli arriva il segnale al nostro.
Adesso arriva David.
Sì, sì, perché io glielo sto già rimandando, però mi devo la conferma. Questo. Quella in cima alla lista c'è una poi 0000 ok. Sono 4 partiti e nella prima sessione subito sì, 4.
Scusami, io lo vedo, cioè io sto su YouTube, io sul
Ok, allora faccio così, guarda, mando, tu stai in diretta?
Sì, sì.
Allora mando la camera, ti mando anche l'audio e la tolgo. Ci abbiamo 20 secondi più o meno. Yes. Così almeno sono sicuro che sta arrivando questo.
Super important. Now I can bring the demo, but that's not
So this is an update.
no, it's not update. You can just modify the items. That is
Okay. Sorry. Vabbè, se lo devo rifare perché mo hai chiuso la pagina che hai fatto, l'hai chiusa.
Ha fatto refresh.
Ah, no, ok. Vabbè, aspetta, lo rifaccio. Ok. Io dico una cosa, devo cambiare la camera così la facciamo simultanea, aspetta. Colleghiamoci.
Check, check.
Provo il podium, l'hai già provato? No, ci ho provato, il microfono. Ah, non hai le cuffie, perfetto. Ah, ok. Ok, perfetto. Che bomba ragazzi. Si sentiva ora? Sì, sì, check, check. Si sentiva, check, check.
Thank you.
Mi sembra tutto molto corretto. Allora questo però lo facciamo giorno 2 Questa è la Red Hall, com'è? Red
Sì, Red
Red
Hall.
Hall.
Red Hall.
Infatti c'è di sempre.
Yeah, check.
Fatta. Sei contento? Ti sei liberato? Sono liberato. Questo peso?
Mo avete pranzo solo di riso. Sì, infatti ho preso il riso.
Ma sì, giusto il sugo se ti può dar fastidio perché magari è acido.
Non si accende. Ah, sì.
Accenderà. C'era poco verde. Dicevo, perché ha così poco verde? È più verde. C'è una camera di presa. Il laser? Il laser sta solo giù? No, sta pure qua.
Dovrebbe stare.
Però c'è le batterie da mettere? Stanno su sto
Sì, le
carico.
batterie servono? Quelle
La
grandi?
batteria grande che è questa, guarda. fatto.
Yes, one moment. We're doing my colleague. My colleague. Sorry.
That's fine. Ready? How was the skiing? It was doing so hard for 3 days. I constantly in my wet clothes. Oh my god, I cannot ski. So for me, it's not downhill ski. It's cross country. Okay. And it's only my second time, so and it's sloping is already like this. I was pushing so hard, and my tricycle hurt so much. But you had fun, I hope. or I also brought Philip with me to go skiing. Ah, nice. So he hates it so much. That's you're mean. I'm not ready for this size. Well, you have like half an hour, so go. Hi, you're Marta. Muria. Nice to meet you.
We saw each other briefly at LPS.
Ah, yeah, true. I'm sorry. I saw so many people at LPS.
I imagine.
And you're at Cesar, right?
Yes.
With
I just
Laura?
did my postdoc with Laura. Yes.
Nice. What's this?
Yes. I took a picture of that when it was on the big screen.
Very good. Nice. Good. So, how do you want to do? You want to introduce the session?
If you want to, as you prefer. It's the first time I did this.
Okay.
As you prefer. And program, yes. Just, I saw that like in some presentation previously, like the first author was not actually the presenter. Do we know if like here we're good and the first author is always the presenter?
I've seen all the first authors around.
Okay, so before I say a name, it's like not the right person. Okay.
Okay, so maybe I can do a brief introduction of the session, and then I introduce myself, and you introduce yourself, and you start the first presenter.
Perfect.
And then we switch. And the time it was 20 minutes, right?
It's 20 minutes, yes, and was recommended if we just say 3 minutes when it's before.
Yeah, maybe let's go for 5 because then
questions. Yeah.
Okay, so 5 and 2. Okay,
Perfect.
What are you working with?
I work on deforestation. For my PhD, I worked on near real-time deforestation detection using Sentinel-1 and Sentinel-2 time series. And now I'm concentrating more on the first disturbance product with Laurent using biomass.
Okay, nice.
So
you probably
Hello. Yeah. Good, so good afternoon. I'm Muriel Pinheiro. I work at ESA Esring as SAR Data Quality Manager, working heavily with biomass data in the development of the operational processors, and as well with Sentinel-1 and pretty much all the other SAR satellites that we work with at ESA. So we start now our session, Biomass First Results number 2. We will have several topics. We start with some evaluation of interferometry. We continue with a couple of presentations in phase triplets. Then some 3D reconstruction with biomass data, and also finalizing with biomass tomography. Here's my co-chair, Marta.
Hello, everyone. So I also introduce myself. I'm Marta Bottani. I'm a postdoctoral researcher at CESBio and ISAE Supero in Toulouse. And I also welcome you to this second episode on the first results with biomass data. So I think we can start. We can open this session. And I would like to give the floor to Urs Wegmugel. I apologize if I completely mispronounced your name, which is going to talk about investigation of P-band interferometry using early biomass data. So the floor is yours.
Thank you for the introduction. So this work was conducted together with Christoph Magniar, Maurizio Santoro, Oliver Kartos, and Andreas Wiesmann. Gamma Remote Sensing is a small Swiss company and with strong focus on microwave remote sensing. Our main activities include research projects. Then we have the Gamma SAR, INSAR, PSI processing software suite. We develop, build, and sell microwave instruments, and we provide services and consulting. Let me start with looking at the available SLC products for biomass. So there's a SCS, standard SLC product, and then also the STA SLC that is co-registered to a SLC reference. So initially we looked at which one we want to use, and the comparison of the STA reference with the corresponding SCS showed identical parameter files. The intensity, on the other hand, looks very similar, but values are not identical, and cross-interferogram shows strong phase variation. So we were a little bit puzzled about this, and we observe issues for the first data lines of some STA data as well. And comparison of the STA with the second scene of the STA stack is showing that the co-registration does not look very accurate. So there are offsets larger than half a pixel, and that of course strongly affects parameters as the coherence. So we decided to use the SCS product. Here the offset between the STA reference and the second scene that should be co-registered is showed, and you see in the azimuth offsets values go up to 2 SLC pixels in the azimuth direction. This may be related to ionospheric effects, of course, but in any case we decided we use the SCS product, so we have control over the co-registration. So here first differential interferogram that we generated over the Amazon region west of Manaus is shown. It's with a 3-day interval and 60 meters, so a short baseline. The coherence for this short time and short baseline interferogram is very high over forest, so values close to 1. On the other hand, over water, it's very close to 0. And both is good news, of course. It means you can do many of the techniques proposed over the forest, and the low value over water is an indication that there is not really an issue with azimuth ambiguities, for example, which would give some coherence. And the image to the left shows the differential interferometric phase. So you mainly see a slight
trend. And if we estimate and subtract this linear trend, we get the detrended interferogram in the center. And if we unwrap it and convert it to line of sight displacements, here indicated in centimeter, we get the result on the right-hand side. So if we interpreted this phase as displacement phase, we get a few centimeter of displacement. With the short spatial baseline, residual topographic phase is no plausible explanation for the phase that we observe. It would translate into height corrections relative to the Copernicus stem of more than 200 meters. So this is not a plausible explanation. On the other hand, centimeter scale displacements, as we obtained, can be explained by water level changes in areas where we have double bounce scattering between vegetation and the water surface. And this would require, of course, a double bounce scattering with increasing water heights, and we can confirm this by using polarimetric decompositions or looking at the HH to VV phase difference. On the left-hand side, we see for the two dates used in this interferogram polarimetric decomposition. Here, the Freeman-Durden decomposition was used. Along the river, you see yellow, reddish, orange colors, and this means it has a strong fraction of red, meaning it has a strong double bounce component. But not only, of course, also a little bit of volume scattering or surface scattering. And the same is confirmed if we look at the HH to VV phase difference. We see the red color, so the positive phase difference indicates there is also a large fraction of double bounce scattering in the reddish areas, and it's in the case of single bounce, we expect a value around 0, so the green color elsewhere is an indication for this difference. So this confirms that in the areas where we saw the phase difference in the differential interferogram, we have a double bounce scattering as an important scattering mechanism. Here I show a few further 3-day differential interferometry examples over Argentina, Siberia, in the Antarctica, and in Egypt. And sometimes the phase looks relatively smooth and boring, and sometimes it looks very wild. And we saw this morning already, ionospheric effects are, of course, very prominent at the P-band and in these days of high electron concentrations in the ionosphere. So let me first look at methods to identify that there are ionospheric effects. So I call this ionosphere checking. So methods applicable for a repeat orbit SLC pair include co-registration offset refinement field and split beam interferometry. And the method applicable for a single SLC is an offset field between azimuth subband images. That was also tried. So here we see the co-registration offset refinement fields relative to a selected reference state. And it's the azimuth offsets which are shown. And look at the color scale. It's not very dramatic offsets in this case, but still it is spatially variable. And in the second example, the 12th of June, for example, it looks quite wild, so small scale changes of the values, while it's more smooth in the other cases. And for other examples, the scale can go to much larger values. So in the left-hand side, it's over Argentina with values within plus minus half an azimuth SLC pixel. And in the Siberia case, it's even going beyond 4 pixels in the azimuth direction. And you can also see that I was not able to perfectly get the offset field. The colors seem to jump a little bit here and there. So the second method would be to calculate split beam interferograms. That is shown here for several examples, and again we see similar indications that there are ionospheric effects present. So the two first methods I showed can be quite easily be applied to identify that there are ionospheric effects present. With the last method, with using a single SLC, I was not successful in the few tests I did. Then you don't want to only know there are effects from the ionosphere, but of course you prefer to correct them, to mitigate them. And we do this using the split spectrum interferometry method. So we apply this split spectrum methodology as described in this reference to biomass. So the chirp bandwidth is only 6 megahertz, so it's not so broad, not so wide. And we use 4 megahertz difference between the two spectral subbands that we use. And to apply it, we need the double difference interferogram. And this one we can easily unwrap because phases are not so different from 0, so it's all in the lowest ambiguity. And then the average or the full band interferogram. And we have a linear combination with the indicated factors, and the factor Z is similar to the factor Z for L-band data with somewhere between the higher and lower resolution ALOS2 modes, I think, if I remember right. So it's not a bad situation, and we have seen the coherence is high generally, so unwrapping is easier, of course, if you have a high coherence. So here on the very left, we see the ramp estimated from a differential interferogram, just a linear ramp. And next to it, we see the ionospheric phase estimated with the split spectrum technique. So it looks very similar. If we subtract it from the differential interferogram, we get the two images on the right-hand side. So minus the ramp is the third one, and subtracting the the ionospheric phase estimated shows the one to the right. The one to the right still seems to have a slight range ramp or phase ramp in the range direction. So if we estimate from this phase ramp and subtract it, we get the best mitigated result shown all the way to the right now. And so this seems to work fine for this case with a very small ionospheric effect. And here is an example with a stronger effect, and it cannot be compensated or mitigated with just a simple linear phase ramp because of the shape. So if we estimate ionospheric phase, we get what is shown in the second image, and if we subtract it, we get again residual linear ramp, and if we estimate this and subtract it, we get again a perfectly corrected differential interferogram in this case. So the mitigation of ionospheric effects with split spectrum interferometry includes the two steps, so the co-registration refinement with an offset field, and then the mitigation of the phase screen using split spectrum interferogram with a subsequent detrending, which I'm not sure if it's related to small errors in the baseline or other factors related to the SAR data focusing maybe. So we applied this then to the stack of acquisitions over this site where we observed the water level rising. So we have these combinations, and we processed all and obtained then this interferometric time series over 6 states. So the first one is the reference, and then we see the increasing line of sight displacement to values beyond 20 centimeter. And I don't have a direct validation, but in the area, seasonal water level rises at this time of the year are typical, and so I have a very good feeling that it's relevant and quite accurate information. So to conclude, the biomass image quality looks very good. Backscatter, the geometry, phase, coherence can be used. INSAR works well. We were able to map decimeter scale water level changes in the Amazonian wetland area thanks to the double bounce scattering, so it was not just open water, but water with trees. And the ionospheric effects are relevant, and they cause geometric effects. They cause significant phase distortions, and so they may affect differential interferometry and tomography, and slightly affect also maybe polarimetry and coherence estimation. The ionosphere mitigation tests at very low and intermediate level of effects showed some success, so we may try soon if we can also use it for more wild cases. Thank you for your attention.
Thank you very much to the speaker, and thank you very much for staying perfectly in the time. So now we would like to welcome some questions from the audience. Does anybody have a question? Yes.
Thank you. I have a question about the correlation products from the ESA, the SDA. You try to use in SDA, and then you go back to the single look complex. Mm-hmm. So how exactly you do for the correlation?
We typically do a first step based on the orbit and digital elevation model. And then we resample the SLC based on this, and then we determine offset field using matching techniques. In this way, we get this refinement offset field, and we have a look at it, and this tells us if there are ionospheric effects. And maybe in the case with very bad ionospheric effects, it's not a perfect co-registration. Then the same procedure should be conducted for small subbands in the azimuth spectrum. Then you could probably still apply it, but it's a lot of processing, and in the end you may still not be happy with the phase that you get. But that's something I will play around with a little bit more after this. Yeah.
Okay, thank you.
Thank you. A small comment from my side, just to emphasize that the data that you're using are from commissioning phase, and there we were for the most part using just geometric registration, so just with the known geometry, and in fact the stack processor chain includes also cross-correlation and also some multi-squint approaches to try to refine the co-registration. There were major changes during IOC. Not everything is solved so far. We will have a next version of the processor in 2 weeks, more or less, that should hopefully stabilize a bit the stack product.
Yeah, it's not an assessment of the quality. It was one example tested, and then it's safer.
No, that's perfect valid. It's just to say, we are still working on the quality of the product, yes. And at least now in production we have as well the cross-correlation running. So this should avoid the big co-registration errors that you were observing, but of course not the fine ionosphere effects. No? And in any case, there are still issues being solved, so still work to do.
Thank you.
Thank you.
Thank you very much. So I think we can move on.
So the
Thank
second
you.
presentation, So the second presentation is polarimetric effects in P-band interferometric phase triplets by Costa. So Serdar is not here.
So yes, good afternoon, ladies and gentlemen. So welcome again. So, and as Muriel said, this presentation this work is work from Serdar, from Noelia Romero-Puig, from Paul Prats, and I'm giving the presentation because if in depth of time this will be proven inaccurate, then I should be the one to be blamed about. So, let's start. Okay, so maybe the perspective of this presentation. The perspective it is we, in the commissioning phase, we were responsible for forest height inversion. Forest height inversion with repeat pass interferometry is subject of temporal decorrelation, even at P-band. And one of the tasks we had in the commissioning phase was to assess if our temporal decorrelation model are right or wrong. And of course, you feel they were wrong. So, but let's start with the data and what they say. So commissioning phase, and we have here a series of 6 acquisitions starting from the end of May, going up till the beginning of June. We look again on Amazonas, a similar site as shown before in the morning, still with rivers. Rivers are very interesting, remember, about the water. And looking on polarimetry, once more, we don't see striking differences. But of course, interferometry is more sensitive. So, and this is now the interferometric coherence between day 1 and day 2, 3 days repeat pass, and the following interferograms are always referenced with respect to the master. So time is increasing. And then we're going to 6, 9, 12, 15 days. So, and what you see is, of course, first of all, the image remains very bright. So temporal decorrelation or low-scale temporal decorrelation for this is not an issue at P-band, but of course you have many shadows, we'll come later on them, and of course you have the dynamic of the river. So you see here, you have this river appears, this is HH polarization, appears to decorrelate over the time, and then of course you see that this part of the river system decorrelates later in time, maybe affected only one of the last acquisitions. So first question, how this behaves in terms of polarimetry. This is HH. In VV, situation becomes more dramatic, and you see much more clear the correlation effect around the rivers, and in cross-polarization, of course, the effect is larger. So we see very clear the correlation across the rivers. You see water, as was mentioned in the morning, and this is one of the reasons of the temporal decorrelation. We can superimpose the 3 coherence maps, the 3 polarizations, just to understand what is the stability behavior of different scattering mechanisms, and you see colors. Of course, across the flooded rivers, so as mentioned before from Urs, you have the dihedral component. This gives you the highest coherence, the most stable coherence, but very interesting about these secondary images, you see that it pops up green. So cross-pole seems there to provide the highest coherence. So we like to understand also the short time chains of coherence. So, and the next step, of course, is to calculate all the 3 days interferometric coherences. And we saw them in, again, superimposing the 3 polarizations. And now the situation changes, of course. So you see now the 3 days to 3 days dynamic, still a lot. This river is going up, is getting flooded or lowering the level only on the first time, and then as time progresses, this river starts, and then this river starts. You see, you have again flowing water through your scene from this direction to this direction as a function of time. So coherence is relatively high, but of course you have all the shadows. Now, in terms of forest height inversion, the question is, are these shadows, are this the correlation effect related, are only impact the coherence level and are neutral in phase, or they are associated with phase changes in between the acquisitions, in phase changes between the scattering mechanisms. And the consequence of this will be in the first case, temporal decorrelation do not affect the phase measurement, so it's a scalar. In the second case, it is a complex number. So one way to do this to check this hypothesis independent of propagation effect, as for the ionosphere, is this concept of phase triplets or phase closure. So simplified, I'm not the right person to speak about this, but simplified, you use 3 interferogram to generate a circle in a 3D space. You are running around, and if you come out on the same point where you started, then you can assume that your phase is widely consistent. But if you come out somewhere else, then something was changing coherently in terms of phase across these acquisitions. So phase triplet was, in this case, a first test to see if temporal decorrelation is complex or scalar. And now we start to see we are on H polarization. You use these 3 acquisitions, the H channel, we make the phase triplet, and it is scaled here from plus to minus 40 to 40. So negative are negative phases, and red, blue are negative phases, and red are positive phases. And you see many colors. Very significant, very interesting to see that across the same river and the same polarizations, the colors are changing. And then we move in time, so we can always use 3 images to generate some of them. You see patterns which are consistent. This is this pattern here, and because it appears here, here, and here, means that it affects this acquisition here, probably. That's H polarization. Next question, is the same in other polarization? What happens if you change polarization? And if you do this, you move on the H polarization, then you see again a very different system. You see different parts of the river affecting different colors. Much more interesting, all these small details here popping up. So think about that you are not anymore at C-band, you are not at L-band, you are at P-band, you penetrate even in dense forest, and you have not one single scatterer which may change its height, but you have a set of scatterers which may over time start to change the phase relation or the height relative to each other. So, and finally, VV polarization, something in between. So here from HH over VV, and now if we compare this with our 3 images interferograms, then you will see that as said, these images, many of these patterns here correlate with the temporal decorrelation. What is this? We believe it's rain, because if it rains, then of course the phase center, the water on the vegetation layer is changing, so this leads to a shift between the phase center of the ground and the volume. So, can we introduce this? Can we use our understanding, our very simple 2-layer model to get a clue about what is happening or not? So can we exclude, at least detect the cases where complex decorrelation occurs? So for forest height inversion, we have this 2-layer model. We have a Dirac on the ground and a volume layer. So we keep this layer like this. So this is what you have. And as you said, as a function of time, as a function of rain, of drying out or of flooding, you may have a different impact on this 2-layer model. So we simplify even more. So we represent the ground as a Dirac, but we take also a second Dirac representative for the volume layer, and we locate them at the phase center height of the volume alone. So we take a complex vertical structure, and we oversimplify it with 2 Diracs. The one is the ground, and the one is the vegetation. And now, for a model, when it rains, what happens? You multiply with a positive exponential, the volume goes up, the phase center height goes up, and you have a change, a phase change between the location of the scattering mechanism in the forest. And if it dries out, then it's like, super simple, multiplied with a negative exponential, phase center goes down, and the distance between the scattering center of the 2 layers decreases. And then, of course, we can apply the same on the flooding. So this is a non-flooding area, this is a flooded area. Of course, if you try to make an interferogram here, you will find the coherence is very low. Why? Because the scatterers are changing. But, as Urs showed before, if the water level in the river it changes, then again it leads to a change to the distance of the effective scattering centers, and this means a coherent phase. Can we model this? So we are trying to simulate this scenario. We're going to go from a standard day to a wet day and back again to a dry day. And to do this, just to prepare you a bit about what you will see. So this is the phase center height or the height change in interferogram 2 with respect to interferogram 1, and this is now the height change or phase change of interferogram 3 with respect to interferogram 1. And the main difference about soil moisture is that here we have to deal with forests. So forests have 20, 25 meters tall canopies. If there it becomes dry, then you expect to have phase center height changes on the order of meters, so multiple or on the order of the wavelengths, which is different than if you're looking in soil, on penetrating on soil. And on the other side, the level of the rivers, Urs said before, is on the order of a half of a wavelength. If you increase the time or another time of the year, then it can be up to meters. So the change, the change in the phase center height of this complex scatterer, it is different in the forest than it's looking for soil. And now, if we try to do this, this is what we get as a closure phase. So we're changing here one wavelength down, one wavelength up, and the same here and here for image 2. And now we have the scenario that from day 2, the phase center height goes up, so image 2, phase center height changes in this direction, and in image 3, phase center height goes again down, then this means we are moving here. So, and then we expect that, maybe yes, that we are moving in this direction. So now, the non-ambiguous part, if you see, it is just plus minus a half a wavelength, one wavelength, and the rest, of course, replicates this. That's a property of the phase. Now we look at the other scenario, so rain, sun, and rain, and then we go, phase center height goes down, and then again up. This means down, and then again up, and then we are moving here. And in this case, you see, you expect to have different signs. But of course, on the other side, that this is only if you move a fraction of a wavelength. If you move more, then you go in this direction, and then your blue can become red, the red become blue, and you see you are very fast, very ambiguous. Why? Because the relative changes are large, even with respect to the P-band wavelength. So now, what I forgot to say, so we fixed the ratio, the power ratio, the ground to volume ratio of the two scattering mechanisms, 0.5. Now, why it changes with polarization? And we know that if you change polarization, the only thing what changes is the ground to volume ratio. And now we start to plot this for different ground to volume ratios. If you like to see what happens at different polarizations, then you see, of course, that the intensity of the pattern changes. And going to small ground to volume ratio, you attenuate the phase differences. Of course, if they're becoming the same, then you are at zero. So this. But in general, one simple way to interpret, who knows if it's right or not, that the differences, the different polarizations, is the different ground to volume ratio, what you expect to see there. And we go to the next scenario, so now the flooding. So now the difference than before is that now the lower scattering mechanism change his height with respect to the first one. If you remember, this order is changing. Now you have here the negative and here the positive trends. And now if you go to a lowering level, you expect to have something like this. If you go to uppering level, you go to have something like this. And again, also here, everything depends on the ground to volume ratio. So now, in general, if you look on this and you expect to have phase center changes on the order of more than a half a wavelength, which it happens on flooding all the time, it happens on rain all the time, then you see that this relationship stops to be unambiguous. So you have this issue of wrapping of phase, which means our interpretation is significantly, it's not straightforward. So we're going back to see it behaves only there like this. So this is the scene which I saw in the morning. So we have here a more dominant river, and again, different river systems. We look on the triplets, HV. So in between days, then you see the dramatic change of the phase center height in between these acquisitions. You see also the multiple colors here, and you see here that our 40 degrees change often saturates. So we move now from HV to double bounce to Pauli 2, and then suddenly, as the ground, the blue, the minus phase becomes positive phase. So the only reason why this has happened, so in terms of the two-layer model, is the change of the mu, the change of the ground to volume ratio. If this is in this order of magnitude true or not, this remains to be seen. And then moving to surfaces, to Pauli 1, then you see that you have a mixture of these situations. Again, that's a question of mu in the individual polarizations. Good. Of course, we are working, we're trying to see if we can use this concept to detect complex decorrelations in now not zero baseline data, as everyone saw, but in baseline data. And then we are looking here still in a very early phase. So we look over Gabon. This is again 6 acquisitions, 3 days from each other. And again, we look here on the phase triplets, always this tree give this tree give this tree this, and this tree this. And then you see that here and here, it is fine, but the more you come in this direction, you start to have strange effects. So you start to see here the mountains, you start to hear this slope. What is this? This is a non-zero baseline. And if you compare the data before, then you will see that the last acquisition here, which impacts this one, has a very large baseline. So non-zero baseline, of course, starts to introduce the change in the phase center heights because you see through different cuts through your volume profile. You expect to have this. Still, the big surprise, rain has a different sign very often. And the question is, remains this always like this? So we don't have the answer, but we can move to the HV polarization. You see topography is blue, widely blue, but the rain cell here remains red. The same here, a bit more red, and here red. So this is the direction where we are thinking. We're trying to understand if we can find somewhere in the data the possibility to address the change of phase center heights in between of the two acquisitions, the non-stationarity problem which we were discussing before. And it seems that in this direction, polarimetry is an important space to look for. So with this, I'm at the end, I hope in time, and ready for questions.
Thank you, Kostas. We have time for a couple of questions. Any questions?
Thanks for the presentation, really cool. One thing I was wondering, so your model consider a change of scatterers in the canopy going down, right? Your canopy goes down. But because the scatterer goes down, should it also bring a different speckle and so the correlation? The point is, could it instead be just a propagation thing? Less light goes, less energy goes through, and so you see the ground volume ratio, you see more ground. What the tomograms say? Do they show going down of the canopy, or they show the canopy get less bright?
In the forest, in general, what you expect is that the basic assumption here was that the power of the two Diracs remain the same. So if it rains, what changes is the ratio of them, because you have a stronger attenuation. This may cause decorrelation, but this is no non-driver. So in the most of these cases of rain, still the coherence is high. Everywhere you have rain, the coherence is high. But of course, this model has to be extended, no question. But if you start now again to simulate the change of the mu from acquisition to acquisition, then it becomes more and more ambiguous. So this was not an attempt to say that this is what changes, but if you assume that you change according to what you expect to have from a rain in distance of phase center heights or in flooding, in terms of flooding, then you are on the order of the phase which you see. If this is true or not, or incorrect or not, this remains to be seen, probably not. The second important point is that if you look on the INSAR data of scatterers at wavelengths, which you have more scatterers inside the resolution cell, then it is not anymore as clear as before what is changing how much. So because you have still to think that you have still a component which impacts the phase distance of these two scattering centers, which is also a dynamic thing, especially in forest or even in ice.
Thank you.
One more quick question? No?
There's something.
Okay, so I guess we can move. Thanks, Scott.
Yes.
Thank
you. Okay, let's move on. I would like to invite Jan Huan from the Delft University that is going to present statistical analysis of instar closure phases in various land cover conditions using Sentinel-1 and biomass observations.
Yeah. Good afternoon, everyone. I think Kostas' presentation really nice. It actually solved some of my puzzle, and you will see it later. And today I'm going to present the statistical analysis of this instar closure phases. So in the past few years, we spent a lot of time to look at closure phases with Sentinel-1 data. So on the left-hand side, you can see this vivid polarized descending animation of closure phases over Iberian Peninsula. And on the right-hand side is the land cover map. And here are three main things. First is from the magnitude of the closure phases, it's not zero. And the second one is this closure phases changes with time. And the third one is that it shows a correlation with the land cover. I think now you may already have the idea what is a closure phase, but I will just still show this part to make it more clear. To construct a closure phase, you need three different images, and you interfere the three images with each other. You got three interferograms, and then you combine the phase of these interferograms in a circular way. You got closure phases, and this quantity is always equal to zero when you are looking at a pixel level. But when you are starting doing the multi-looking for your interferograms, you are mixing these scatter families with distinct phase behavior. Then this expected value of this closure phase is no longer zero. Maybe you are thinking maybe it's just a phase noise, but if it's phase noise, when you average enough, the expected value is always equal to zero. So can it be these geophysical changes? To answer this question, we did a lot of research and also dive into the literature. Indeed, this closure phase is a combination of phase noise and geophysical variation. For the geophysical variation part, it's a complicated story, so it had three main different reasons. One is the dielectric variation, and another is the volume scattering in combination with a perpendicular baseline. And the very new one that we find very recently is a differential movement within the resolution cell. Today we will only focus on the phase noise part. So you already see my Sentinel-1 closure phases. Now you may ask how significant are these closure phases. This plot I show here, the y-axis tells you the fraction of the cells which exhibit significant closure phases. You can see among all these different land cover types, there are always 20 to 16% of cells will exhibit significant closure phases, although this number will change over time. Another thing to notice is that this significance shows a polarization dependence. Normally in copal is more significant in crosspole. And it also shows a land cover dependence. In the cropland, the cells are more significant than in the forest and in shrubs. Now we want to see what would if we would see the similar things using biomass observation. To answer this question, we make three hypotheses. The first one is, of course, we will assume we will see this non-zero closure phase also in biomass observation. And those observation is statistically significant, and it changes with local conditions, for example, the land cover types. So now we are changing from Sentinel-1 to biomass commissioning data, L1C, which means we are changing frequency from C band to P band, and we will have full pole observation. And if we trust ESA did a great job, we will have 0 baseline data. And the temporal resolution changed from 6 days to 3 days. And the example I show for Sentinel-1 is about 16 images per stack in 2017. But for this L1C data, we only have 5 images per stack. Another difference is we changed from Iberian Peninsula to some case study in South America. So from this information, it's not really comparable between the 2 data sets, but let's see if we can find something in common. So I choose 4 different sites, from Amazon forest to mountains. So from left to right, the density of vegetation is decreasing. And now we look at the closure phases. This is over Amazon forest. If you compare with this Google image, you can see the rivers, and there are also more detailed information over these tiny rivers, like this blue one and this small red one. And then this is cropland, but in cropland, this data is in June, so in Argentina it's at the beginning of the winter, so basically here we see the soil. And this is shrub and mountains. And you can see from all these examples, even when the vegetation density is decreasing, the non-zero closure phase is always there. Now you will ask, how do I know if this observation is significant or not? To answer this question, we make a null hypothesis, which is the closure phase is solely contributed by phase noise. So we use a numerical model, which we take the 3 coherences and 1 equivalent number of looks as input to do the numerical simulation to calculate the standard deviation of closure phase, assuming it's only contributed by phase noise. And then we use this quantity called the significance ratio. So if we assume this closure phase is purely noise, when we normalize this observation, this quantity will tend to be a normal distribution, which means if we say anything which is deviated from this distribution, we can see our observed closure phase is significant. So now we look at our closure phase example again, and we plot also the significance ratio. So from the significance ratio, you can see this statistically significant closure phase is everywhere. And here, this river, this visually noisy areas, such as this river, they exhibit a very low significance ratio. This is mainly due to the very low coherence. And then another interesting thing here is that in the closure phase observation, you see big closure phases, but they are actually not that significant. But this one near the mountains, you can see very tiny little closure phases, but they are quite significant, which indicate that even when the signal is very small, but our signal to noise ratio is very high. Now the question is, would this significant changes over different conditions? To answer this question, we use the 5% false alarm in noise-only scenario, and then we compute a fraction of cells which exhibit significant closure phases. Because it's a 5% false alarm, which means when your P is larger than 5%, you can see this geophysical closure phase as statistically significant. Now we look at the Amazon forest again, but using all the polarization. Because this Google image is hard to see, so I also put the biomass preview here. So in the middle region is similar to what Costa shows. This is floating error, and because of this power rack changing of different layers, you can see the flip side of these closure phases. So this is a very clear example that closure phases will exhibit polarization dependency. And now we look at the numbers. And in this specific area, there is a very big difference between the number of cells which exhibit a significant closure phase. And then is our cropland. Here you can see HH and VV are very similar, but in cross-pol, there is something looks like it corresponds to the cropland location, but we're really not sure if this is just an artificial noise or it tells you some geophysical signals. But it seems like in our significant ratio, we kind of diagnose it as a noise. And for this region, this fraction of significant cells are similar in all polarizations. For the shrub, we can see this signature is consistent over all the polarization, but there are more significant cells in co-pol than cross-pol. And the last example is in the mountains. This preview is a bit hard to see, so I remove it. Here, the HH and VV are also very similar, but cross-pol, it shows a bit of different behavior. And also, we see this difference in the number of significant cells. Now we want to change the combination of the images to construct the closure phases. What we had now, those you have seen, is with this highest temporal baseline, 3-day, 3-day, and 6-day. And now I change it. I use this combination as well, which is 6 days. And then I switch a second image to the day 9. So we will have three different combinations. Now I relook at this area of cropland. Here you can see with, when you use different images to construct your closure phases, the magnitude of your closure phases changes. And you can, this is also exhibiting the significance ratio. This means the difference between your observation really matters. And we see the similar thing in the sharp region at H. It changes from negative to the positive, as well as the significance ratio. But for this mountainous area, for co-pol, it's actually quite consistent. You don't really see this very big Filippo sign, but in the cross-pol, you can see the closure phase from 0 to negative. Now you look at the numbers again. So for each specific temporal baseline combination, the rank of order of the significance in polarization persists. So for these vegetative regions, there are always a similar order of significance, but in the mountainous area, the cross-pol has a less significant cells. And if you combine different combinations, the magnitude of this fraction also changes. And here you may already notice there is, I would say now it's an outlier, but we still need more data to confirm this, if it's a really outlier or not. Now we can revisit our hypothesis. The first one, we did observe this non-zero closure phase in all the selected sites. And over all the selected sites, we observed at least 20% of a closure phase, which are statistically significant. And the last one is what you just saying. This magnitude and significance of closure phases varies with in time, space, and polarization. As we are really at a very starting stage of our project, so what we're going to do next is to try to do what Kostas already did, is to combine these images using different polarization to see how many layers we actually see with this quantity. And then we would like to have more geophysical information to try to interpret what we see. And lastly is to have a longer time series, because in our Sentinel-1 observation, we really see the seasonality of vegetation growth, where all kinds of informations. But then we need have the challenge that we have to deal with this non-zero baseline. Yeah, thanks.
Thank you.
Thank you very much. Thank you very much. Is there any question? Yes. Can we have a microphone? Thank you.
Is there a special reason that you don't show maps of the closure phase with the less reliable parts masked? Because you also have the map of the statistical reliability.
You mean why I selected those sites?
Could you apply the reliability to generate the mask and then show
only the significant
closure
part?
phase with only the 20% which are reliable, or the 40% which are reliable?
Yes, we can apply this mask to this
Because
closure
it
phase
may
observation.
change a lot for the, when you see the reliable parts, maybe you're closer to interpreting it.
Yeah. We did this for Sentinel-1 observation, but we haven't reached there for the biomass observation yet. But we would like to do it. Yeah, thanks.
Thank you. Is there any other question? We have some time.
In your closure phases, there was also some clear ionosphere stripes.
Which one? Do you remember the site name?
When you had the plot with all the phase.
This is very slow.
This one? The other one, no. Okay. One more. The first ones. One more.
This one?
No. One more. In the first part of the presentation.
You mean the one with the Amazon forest?
Yeah.
Okay, wait a second.
At least, yeah, there you start to see some things, no? You see a bit the diagonal lines. So is this something that you're expecting?
I'm not really sure, because this one is also a very clear separation of different land cover, because at the lower part is clearly the crop land. You can see it from the shape, it's very artificial shape. But on the top is more natural. So I'm not sure if this the separation is artificial or natural.
Yeah. I don't know, I had the impression there, and also in the previous one, I think that you were seeing some diagonal stripes that to me were looking like ionosphere artifacts.
This one?
Maybe I'm wrong. But we can talk about it later.
Yeah.
Yeah, there, for example, you see a bit on the top here, especially on the HH at the top, you see this kind of vertical thing. That to me look more like ionosphere.
Yeah, it could be. But it also can be the artificial effect of processing.
Okay. Good. Thank you very much.
Thank you.
So we move to Matteo, who will present Biomass 3D repeatability reconstruction for forest structure mapping early mission results.
So, thank you. Good afternoon, ladies and gentlemen. So, I would like today to a bit share with you some impression that myself, but also my co-authors, Roman Guliev, Noelia Romero, Felipe Betancourt, Pau Prats, and Kostas Papatanasiou, had about biomass tomography. Biomass tomography has become a reality already in the commissioning phase since the beginning of October. And so we already start to have data sets in different places in the world. And of course, the curiosity was very high because it's the first mission that gives you tomography from space and at large scale. The resolution is what it is, but when you have large scale, you will see that, of course, this large scale compensate already at some extent. But let's start from the beginning. So if you like to make tomography, first of all, you need to take a scene. We took the scene of Gabon. I think you saw this scene today already several times. So you start here, you have Angola, you end up, and then you go north, and here in the north you have La Lopé, the national park in Gabon, and also your forest changes a lot from south to north. Then, if you like to make tomography, you need baselines. Without baselines, there is no tomography. So, and therefore, this is what you have. This is COM5. The first acquisition was the 6th of November, the last acquisition the 18th of November. And you see that the baseline basically progress with time. They get larger with time. They're almost uniform baselines. There are a few deviations, but they are not you will see later that these are not of concern. But with this, you will be able to get, of course, it's not a full tomographic stack like Biomass will give, but so you miss 1 or 2 images, but you see that already with this, you are able to get a vertical resolution in the order between 20 and 30 meters, and I hope I will convince you that you can start to do something. So now you have the scene, you have the baselines, you start to calculate coherences. What I was doing at the beginning, just to calculate the coherence between consecutive pairs. So that's the first pair, 6th and 9th of November, 9th and 12th of November, 12, 15, 15, 18. Well, it's a story that you already know quite a lot. You see here, this is the surface that you have here, but there in the forest, and in many places, you see that is the coherence. So the baseline is always the same, but your coherence is going up and down because of temporal effects. Temporal effects that change the underlying reflectivity profile. This is what you, of course, what you may think. And you see here, for instance, you have this area here, which is very black here, but so you have a decorrelation here, which is not present here, a bit milder here, and then again, something stronger. Of course, you have decorrelations along the river, some other decorrelation here, something here. You see, you have these decorrelations which are localized in space, but also in time. So the coherence can also come back. But in general, if you have a reflectivity profiles that changes, you can ask yourself now with tomography, which reflectivity profile do you reconstruct? So because in general, you like to have one reflectivity profile and to reconstruct that reflectivity profile. And now the question is, indeed, so will, in a situation like this, repeat pass where you combine acquisitions with different underlying reflectivity profiles, in a situation like this, will tomography still give you some information about vertical structure? So let's make maybe something which is trivial. So if you like to reconstruct a profile, normally what do you do? Of course, you calibrate your data. After you calibrate your data, you calculate a covariance or coherence matrix, and then suppose that you like to focus with just a plain Fourier, you just then basically you make all the calculations, you come to an expression like this. It's a Fourier transform if you like, but then you can also make something, you can just see this relationship in a bit a different way. You can start to work in diagonals. So you have the main diagonals where you have all ones, and then you have the diagonal above the main diagonal, and then again and again, and you see you end up with this sort of expression. So, and in the case in which you have, let's make the ideal case in which you have uniform baselines, then if you have uniform baselines, basically this difference is always the same. For this diagonal, you always have the same difference also here for this diagonal, but it's only at different values. But the idea is that now, when you calculate your profile, what you do, it's like you make looks also across the diagonals. So, and these are looks in time in this repeat pass implementation. So now, with Biomass, you don't have baselines which are exactly uniform, but you have baselines which are almost uniform. So this doesn't apply one-to-one, but still, there is a part of this still survive. So this means when you make tomography, in the end, you work like with the average along the diagonals, or something which is close to the average. Now, if I take the coherences at the beginning, I calculate the average, I get something like this. So, and you see now, of course, you don't have it's just an average of those. You don't get the largest coherence, you don't get the lowest coherence, but what you see is that now the coherence is something which is also spatially a bit more homogeneous. The question is, so if this is something that allows you to at least attenuate all the temporal variation, the question is, when you make this process also on the other diagonals, do you get now something which is meaningful? So in principle, now this is, if your scene was stationary, this is what you would have. So for all the acquisitions, you have the same profiles. Now you make the averages across the diagonals. You see all the diagonals, they take averages of the same profile. And now you start to have a change. The simplest change is just you have a ground which gets stronger or weaker. So this is something that it's easy. So it doesn't change, for instance, the profile of your volumes. If you start to make averages, basically, in the end, what you get just an average contrast between your ground and your volume. But this means that you change the radiometry of the profile. So you still have a geometric information. You don't change the phase centers of the separated contribution, but it's just the radiometry that gets averaged somehow. And you change this contrast between, for instance, here the ground and the volume in the end. But then you make this in one polarization, you make this also in the other polarization. So in this sense, you also change the contrast between, or you may change the contrast between the polarization. Of course, this is an easy case. You may also have the more complicated case in which it's just all the phase centers here which are changing because they are subject to attenuation somehow. And therefore, at this point, it's a bit more difficult to characterize what happens. So, you know, you can start to simulate and see, to look for trends. But I think the best, in the end, is just to open the data and to see what's in the data. So let's say so we took just this line along azimuth. First of all, we calculate, as always, the point spread function just to have an idea about the tomographic performance. Point spread function, which is very stable along azimuth. So this is what you read here, it's azimuth. So I was reporting also here. This is a line which is around 13 kilometers. Point spread function, it's perfect. So basically, the first side lobes is above 100 meters. It's 100 meters above the main lobe, so this means that whatever is between minus 100 and 100 here, it's okay, so you don't have any focusing artifacts. Then you calibrate the data, and then you plot, you just make a Fourier profile of the data in the same heights. And you see basically this is where your profiles are, this is where your scene is. What you see here, these are just side lobes which are related to the side lobes of the point spread function, so there is no artifact. In general, you can also apply now to do something a bit better than the Fourier. You can apply a Capon, and the Capon works, so in the sense that can still attenuate these side lobes, which is something that's fine. So it's something that if data were good, you would expect it. The question is now, yes, let's take maybe instead of having this wide height range, we take something smaller. So now we also try to steer everything at the ground. And now here you have the Fourier with the three different polarizations, HH, VV, HV. Now you see in HH you have quite a strong ground, which is located at 0 meters where you want it to be. You have some volume returns here. In VV, the ground reduces because now you expect not to have there the dihedrals, and this is something that you see also in the data. So somehow the ground in VV is there, but it's less strong than in HH, and in HV you have the lowest ground. You can also again apply Capon. You expect that Capon also gives you something more in the resolution, and exactly what you have. And you have also the relationship across the polarization. So biomass tomography is good. Despite the fact that you have these changes of the profile, it's somewhat, at least in this case, it's somewhat attenuated, and you still keep this consistency across the acquisitions. Of course, you can go ahead and you can try to optimize polarization, to try to maximize the ground or maximize the volume, and you get that. The question is now, having this profile, are they meaningful or not? Do they show something about the forest structure or not? Let's say so, there is no way to, or at least it's very difficult to get an idea about this, even but this is a way that you like to try this way because you cannot even validate a simple reflectivity profile. So therefore, the best thing, or at least one thing that you can do, is to go where you know the forest, you know what you may expect, you maybe have some LiDAR data, and then you take your profile and you try to see in the radar profile if you have those characteristics of the forest that you interpret from your ground measurements or from the LiDAR. So we are in La Lopé. La Lopé is something, so Gabon, it's something that it's quite well known since several years, since the first AFRISAR campaign. And we have ground plot there, and we also know where to look structural differences. So we go here around the savanna, we take one inventory plot. In this inventory plot is a colonizing forest. In the colonizing forest, you see here the Elvis profiles. It's a very open canopy, and you see indeed that the LiDAR penetrates a lot, and the peak of the LiDAR basically moves. So let's say, so it's not localized, but moves. What happens in the biomass? So let's say, so if you take HH, you have the ground is dominant. If you take HV, the ground is not dominant anymore, but you see indeed that different profiles in the same area, different profiles, they give you basically a different top boundary. So, and this you can maybe you can interpret it something like which is consistent with this situation. You can take an Okume forest where you have this canopy which is very thick. Indeed, the LiDAR cannot penetrate very much. You go at P-band. P-band penetrates also here. So here the comparison between LiDAR and P-band becomes more difficult. But you see that here the situation is different than this one. So now you have profiles where your volume return starts to be intense. And you know, it's also quite localized for several profiles around 40 meters. And then you go in a situation which is very, very if you like, very, very complex, because you have all this return, even the LiDAR profiles, and this complexity is reflected also in the radar profiles. So somehow, at least for these three different situations, you have profiles that can be matched to that situation. You can also go to the maximum volume profiles, and there you have also the same thing. But of course, that's a bit of a different discussion, because here you need looks for this. You need looks. Here, for instance, we are operating with a multi-look cell of 100 by 100 meters. The question is, what happens if I change my looks? And you will understand in a while why I like to change the looks. What happens if, for instance, instead of 100 by 100 meter multi-look cell, I use a 50-meter multi-look cell? Now, these are Capon profiles, for instance. Capon needs looks. And in this case, you see that since it needs looks, then the inversion now starts to be a bit shaky. And therefore, you see that basically, also in the situation in which the forest tends to be more homogeneous, in this case, with these not so many looks, you start to see an heterogeneous forest. But you can also go to 200 by 200 meter looks, but now your forest looks the same on a different end. All the profiles are the same. You don't have any more this, for instance, this inhomogeneity at the top, this inhomogeneity here in the volume. Now it's very much smooth, so you understand already that these 200 by 200 meters that make your profile reconstruction better, make your structure reconstruction worse. But of course, speaking about structure now, we make the last step. We have the profiles. What can we do? Let's estimate structure. To estimate structure means to be able to discriminate this situation with this low complexity from this situation with the highest complexity. In this situation, your profile will look like this. At the other end, they will look like this. So it's a statistical, in the end, it's a statistical game. So in which you reconstruct your profile with a certain resolution, and then you like to see the relative variation of the profiles in a larger cell. But now you understand that if you like to be able to see, to reconstruct structure and to see this variability of the profiles at the right scale, you know, normally people, when you ask them at which scale you like to see structure, they tell you 100 by 100 meters. But now you have profiles which, you know, they are already at 50 by 50 meters in the best case, but with 100 by 100 meters, of course, you get something better. Now you see that if you like to have a meaningful measurement of this variability, now you need larger cell. So that's a discussion that will take longer, and for sure it will take a lot of work in the next month. But to give you an impression, now I took profiles at 100 by 100 meters, and then I calculate structure at 500 by 500 meters. The purpose is not to see local structure, but to see a structure gradient along a transect of 1,500 kilometers that goes from Angola to Cameroon. Do you see difference? And this difference, do they show patterns? So indeed, they do. So you start with, we take just a Fourier beamforming. You see that you have the largest structure is here in Gabon, in the highest in the fattest tropical forest, and then you start to have a descending gradients of structure. So your forest becomes less and less complex. Of course, in the surfaces you have no complexity. You change polarization from HH to HV, you attenuate the ground, you hope to see better your canopy. Indeed, it's something that happens, so you see here, this is a bit more noisy, and you start to recover some points here. That's just because, and this is, of course, it's a forest which is also shorter, and therefore you gain something in terms of resolution. If you like to push on resolution, you can also try to use the Capon, same story, so it's the same trend, but now you start to fill more and more areas, and therefore you hope in this way maybe you are able to characterize better your gradients. This is not validated. We would like to validate it, and let's see. Of course, we cannot validate this large trend, but what we can do, we can focus on a smaller area. So again, in the National Park of Lopé, we have Elvis acquisition of 2023. There are 2 years difference, but for structure in a national park, it's not an issue. So this is height. The height is rather homogeneous, and this is structure. And structure is not as homogeneous as height. And you see here, for instance, you have stands, which are, I don't know, around 40 to 50 meters, all of them. But here you see that structure, you have areas which are less complex than others. So the structure that you get from the profiles does not necessarily correlate with heights. So this means that you have an information which is complementary from the profiles to the height, which is what you would like to see actually from structure and especially from tomography. So, in summary, Biomass Tomosar works, and we are all very happy, at least here. So we need to see a bit more in all the different data sets. The only way to do this is to process more and more data. We need to understand a bit more what this scattering non-stationarity means, but it looks like tomography might be robust to it. And also these profiles, they are not just a shape, but they also have a structural, maybe they have a structural information. And up to now, this first attempt was, I would say, even surprising, but we need to see more. And this is what we are going to do. So, thank you very much. Sorry, I know I was late, but I hope it was interesting for you.
Thank you very much, Matteo. We had a bit of margin, so we have time for a couple of questions. So, any questions? People?
Is it working? Oh. Thanks for showing the nice tomograms. One question. So on the examples of tomogram that you show, did you look at the stationarity of your scatterers in each zone? I mean, was it a zone affected by this kind of closure phase issues with the variability?
No, we did not look yet, but for sure we had these changes of coherence, so we guess you will also have this non-closing triplets. Of course, the idea is, do these phase triplets tells you something also for tomography? Not in terms, maybe not for compensating the non-stationarity. This is a different game. But at least, you know, to have an indicator, something. So.
Any other question? One more? No? Good, so thank you again, Matteo.
Good, very thank you. And so I will introduce the last speaker of this session, which is Francesco Salvaterra from Politecnico di Milano, who is going to present us with some first tomographic results with the Biomass mission.
Hello, everybody. I just want to conclude this session with a short presentation, which is a bit qualitative, but showing nice images about biomass tomograms. So I will show the processing chain starting from level 1 images, going through the stack, the calibration that we do, and ending with some tomograms directly from biomass. So, okay. So the processing chain specifically starts from a stack biomass level 1A images. So we take a few of them, 7, in the tomographic phase, and we proceed with co-registration and stacking, and then with the calibration phase, where we compensate for the ionospheric disturbances, and we create the level 1C stack. Then for performing tomography, we need an interferometric product. So we proceed with ground steering, where we eliminate all the phase differences so that the ground goes to 0 in the tomogram, so that we can perform then tomography and produce the tomographic results. So starting from the stacking, we take level 1 data, as I said, and we perform a 2-step co-registration. First, a geometry based on the orbit and the DM, and then we refine it with speckle tracking adaptive co-registration based on cross-correlation of the image. So you can see, I said, it will be a qualitative presentation because I'm going to show the images through the whole step. So we start from 6 images in this case, level 1A, and then after co-registration we get we increase the coherence, of course. Now they refer, each pixel is referred to its position in the images. This is an example of Papua New Guinea in October, and it's really nice for its low ionospheric presence and because co-registration works really well. Now, it works really well apart from several when the ionosphere is very, very strong. These are some examples. Above you see in Amazonia, we have very strong scintillation. I didn't even put the coherence because you see it's in the Pauli representation. And then below you see 3 images over Antarctica in November. And here is a pair data set over Antarctica in June that Stefano presented this morning. So in this case, co-registration fails because the images are defocused, not just shifted. So what we do, as Stefano explained this morning, we applied the multi-squint correction. So we calculate for each pair a 3D coherence. So we calculate the coherence as function of the range, the azimuth, and the squint. So, and then we look at the phase of this coherence, and we recognize specific trends. So disturbance at a certain height have specific trends in the phase. As you can see, this is the image before. Here there is not so much ionosphere, we see vertical stripes, as Stefano showed this morning, while here there is some slight ionospheric disturbance, and we see some trends, some sloped lines. So this is a section of the multi-squint phase indicated by the line. Here is the squint dimension, and here is the azimuth. So making things short, we can identify the layers and their disturbances and correct them from the image. So we have a choice now. So we can choose if co-registration is fine, we can go with that. But then if there is ionospheric disturbance, we can choose to correct it as a single layer by focusing to ionospheric height and refocusing, or if there are multiple layers, we will correct it by subband refocusing. And as you can see, even in very strong ionospheric cases, the coherence is well recovered. Now we have a stack corrected by ionosphere. The problem with that, as Stefano said today, we are left with some low pass phase screens that a multi-squint is not able to recognize. It's blind to them. So this is not a problem for tomography, because we really need an interferometric stack. We need a relative phase, not an absolute phase. So we can correct the stack applying two types of calibration. We can apply phase linking calibration, where we try to find the equivalent phase center of the whole stack, find its phase, and then correct so that each image in the stack is referred to that phase center. So this is data from a FSR campaign, just not to make spoilers. And in this case, we will have the 0 at the equivalent phase center of the scene. Otherwise, we can do SKP calibration, which all the tomograms you will see next are calibrated using the SKP, where we use the difference in polarimetry and baseline to separate the scatterer's mechanism, find the ground, and put it at 0. So for this calibration method, we will have ground at 0. Then we can also, if needed, refine this ground steering step using high-resolution spectral techniques just to have a better steering towards 0. This is necessary, for example, if you want to do ground notching tomography. And so this is the effect. This is a stack of 5 images over La Lope in October. And as you can see, this has a block structure because one image is missing in the acquisition, was missing in the map. So we went on with that, it was fine. And also, this image is affected by ionosphere. And as you can see, it left very peculiar low-pass phase screens that got corrected. And so everything can proceed to tomography. So how we do tomography? We can do beamformer tomography. It was explained in the presentation before mine, which has the advantage of giving radiometrically corrected results. Otherwise, we can do Capon tomography, which is a super resolution technique, and it also rejects side lobes, but it gives not so accurate radiometrical results. So now, to biomass data. I will start with the stack, a nice stack over Tumucumaque National Park in the border between Brazil, Suriname, and French Guiana. So this is a very good stack with very regular baseline acquired in October and very precise progression of the critical baselines. Also, not significant disturbances in phase, in ionosphere. So a really nice example for a stack. So these are the Pauli images for all acquisition. They look really beautiful as all biomass data. And then focusing with beamforming, we obtain for the different polarization these results. So as you can see, really nice tomograms. I've put the section where I took these tomograms, and they really overlap with the features you see in the Pauli. And then, so to see how nice these results are, I've put a slide where I publish, I refer to a web story we did with ESA in collaboration with LR, where we took this data and we did a Pauli slice at constant height. So this Pauli slice, I have to say, are realized by DLR, and they did a really beautiful job. So as you can see, the difference you can see in this Pauli at ground height plus 30 meters and ground height plus 60 meters, the nice change in scattering mechanism and in color. I want you to focus also at this image, ground plus 60 meters, not for the colors, but for the lack of colors, where the trees are low and over the rivers. It's really nice, it's really dark, so the tomograms are really well focused, and that's beautiful. Then I want to conclude with another stack. I've returned to Lalopé again. So as I said, at the time when we downloaded the stack, we didn't find an image corresponding to I think was the 13th of October. It was missing from L1 data, but it's a really nice example of stress test, let's say, what we can do with a not-regular baseline. It's curious. Also, this image, as I said before, was affected by ionosphere. We corrected it. There are left some really small stripes. I don't know if you can see them, but it's really fine. And so these are the Pauli images, all fine. You can see here some ionospheric stripes, and you can recognize them by now because all day you have seen them. And these are the tomograms. So this is beamforming. These are really good tomograms. Also, it worked perfectly even with a missing image in the middle of the stack, and it's really the best time to show also Capon because it rejects side lobes. So in this case, it gives very similar results, also nicer results. And as you can see here, there's a mountain, some rivers, and you can see all the features in the tomograms for the different polarization. So to conclude, we have a really nice instrument. It gives really nice tomograms, I'd say, and also really robust. It's really robust to anything that may happen. We focused a stack with one missing image in the middle, in presence of strong ionosphere, so everything is going fine. So if you want to know more on this processing, well, this morning there was the ionospheric correction from Stefano. On Thursday, there will be the ground steering strategies. We will delve deeper a bit, also showing all the fine steps to obtain that. And also, if you want to see additional tomographic results, there will be a couple of presentations on ice tomograms and tomographic products on deserts. Also on Thursday. And that's it. I'm finished.
Thank you very much.
Thank you.
Thank you very much. Is there any question? No questions? Maybe somebody has a question? Yes.
And I want to ask what's the size, multi-look window size you used, and the single look or the window size? Thank you.
Okay, for tomography, we used 200 by 200 meters.
I don't hear clearly.
200 by 200 meters, so windows.
Okay, thank you.
Thank you. Any other question? Maybe I just have a curiosity. You said it was qualitative, so I assume it was not validated. Do you have like a plan for validation? Do you have like plots, ground measurements? Is it possible to actually validate large-scale products?
We're waiting for validation data. For Tumukumake, I guess it will stay like that because I've been told that it's really hard to reach as a zone, but in Gabon, for sure, we will perform validation and put a LiDAR on it.
Okay.
But then also it was a dirty stack, just a proof of concept to see what the tomography looked like in worse conditions. So doing validation on a bad stack, maybe it's not.
Thank you. Maybe we have time for another question if someone has a last-minute question. Yes.
Thank you for the presentation. So because we were talking about the topic of validation, my question is about how do you plan to validate the effectiveness of the correction for the compensation for the ionosphere, right? And what kind of tests you're going to do it for that, and if that will be reported in the image, depending on how much interference you have, and if there are going to be quality flags for that.
Okay, for the validation of ionosphere, we'll just we'll take a look at the results, how the coherence is, how the tomogram results, and also what effect it may have on different targets. Like, for example, the multi-squint correction is like fundamental for Antarctica, and so we will see on those products how they look, the tomograms, how they look, the interferograms after the correction. Then as I said, we'll have the residual phase, and that's still an open problem, not for the tomograms, but for an absolute phase. And there we will work towards injecting some ionospheric external measurements into this estimation and check how they work.
Okay, thank you.
Just to complement, and of course all the work that Francesco and Polimi and DLR are doing are indeed going to the processor, and for each module there are indeed quality flags that try to show how the correction works. They have limitations, but they will give you an indication at least of the quality of the data. There is the same for level 1. Stefano?
Just to complement, so I don't really know how to validate ionosphere correction. I think that the best tool we have is to see coherence, if we just co-register or if we do a correction. Because we see that coherence improves, and also we see that we stop seeing the ionospheric stripes, and we start to see shapes that make sense. But let's say that if you want a quantitative validation, a histogram of the coherence at this point is the best we have.
Thank you. Okay, one last question.
Thanks for the presentation. A technical detail. In Capon, you use the diagonal loading, right?
Yes.
Do you remember what loading coefficient you use in comparison with the thermal noise level? Really a curiosity or a very technical.
Yeah, I'm sorry I don't remember the specific factor. It was really small. It doesn't need to be too high. Okay. Just almost
thank you.
Okay, thank you all the speakers. Thank you, Francesco, again. Thank you to all the speakers, and thank you to the audience for the questions. I think we can wrap up the session, and I remind you that there is the poster session in 10 minutes at 4 o'clock. And
now
thank
coffee
you.
break, no?
And now coffee break.
Can I also remind you of 2 more things? Sorry for interrupting, for jumping in. At the poster session, there's also Roberto, who has a desk. He's the map guy at the ESA. So if you want to access the data through the map and you haven't managed so far, go to him, ask him if you work already with the map, and if you want to see some specific features on the map, some tools on the map that are not already there, go to him and make him a recommendation. And there's also a desk where Olivier is sitting. Olivier is building Polinsar Pro Pi. So if you have any wish for Polinsar Pro Pi, go to him, tell him what you need, what you want, and he will try to implement this. Thank you.
Thank you, Klaus.
Thank you, Klaus.